Welcome to another deep dive, everyone. This time, we're going headfirst into the wild world of Fourier restriction theory.
Always a fun place to be.
It is. And we're focusing on a particularly fascinating paper by Wang and Shukun Wu. Now, this area has some serious implications. Talking signal processing, number theory, the works. So are you ready to unravel this with me?
Absolutely. It's a challenging area for sure. But this paper is really insightful, especially when it comes to the Fourier restriction conjecture, something that's been a real head-scratcher for mathematicians for decades.
It really has.
Yeah.
You know, to put it simply, this conjecture basically asks, can we really understand a complex wave just by looking at how it behaves on a specific curved surface? It's like trying to figure out an entire symphony just from the music escaping through a tiny crack in a door.
I love that analogy. Mathematically, it's about understanding the relationship between a function on a surface and how it extends to the entire space. Wang and Wu, they use some really clever techniques to tackle this. We're talking decoupling theorems and 2n's Furstenberg inequalities. Really powerful stuff, particularly when they apply it to the three-dimensional case.
Before we get too deep into the weeds, can you give us a quick refresher on the Fourier extension operator? That's kind of at the heart of all this, right?
Absolutely. The Fourier extension operator, we denote it as E sub sub, and what it does is it takes a function that's defined on a surface, S, and then extends it to a function on the entire space. It does this using the Fourier transform, which, if you remember, breaks a function down into all its individual frequency components.
So like separating a beam of light into all its different colors with a prism?
Exactly. Each color would represent a specific frequency. And, going back to your symphony analogy, it's like taking the sound waves coming through that tiny crack and then using them to try and reconstruct the entire orchestra playing inside.
Wow, okay, I'm starting to see the picture here. And the restriction conjecture basically wants to know how much can we actually figure out about that full function, the whole symphony, just from what we're hearing through the crack.
You got it.
Okay, now I know that to measure this, mathematicians use something called LP norms. Can you walk us through what those are? In this context, I always get a little fuzzy on those.
Sure. So LP norms, think of them as a way to measure the size or the magnitude of a function. You're basically quantifying how much it deviates from zero.
Okay.
Now, the restriction conjecture, what it says is that for a certain range of these LP norms, the size of that extended function, the one we got from the surface, can actually be controlled by the size of the original function on the surface itself.
So sticking with the symphony analogy, it's saying if the music leaking through the crack is pretty quiet, then the whole orchestra can't be too loud either.
That's a great way to put it. At its core, the restriction conjecture is trying to establish a precise mathematical connection between that original function and the extended one.
Got it. Now, Wang and Wu's paper digs deep into this conjecture, but there's a whole history behind it, right? What are some of the big breakthroughs that led to this research?
Oh, absolutely. One of the early wins was Pfefferman. He actually managed to fully solve the restriction conjecture, but only in 2 dimensions. This was back in 1970. But things got way more complicated when you started adding dimensions.
Yeah, more dimensions, more problems, as they say.
Right. But Tomas made some serious progress using the TT method. He was able to find a partial solution, but only for certain LP norms. So mathematicians had the flat version figured out, but the higher dimensions, those were a whole other beast.
And then comes Bourgain in 1991, right? He kind of revolutionized things with his introduction of wave packet decomposition.
Exactly. It was a game changer.
I remember that term from when we're prepping. It's basically breaking down a complex problem into smaller bite-sized pieces, right?
Exactly. Imagine trying to understand a musical chord. It's a lot easier if you separate it out and listen to each individual note, right? It's the same idea here. Instead of tackling this complex wave all at once, we break it down into smaller, easier to manage components. We call those wave packets. Each one behaves a bit more predictably, making things a bit easier to analyze.
Okay, that makes sense. So wave packet decomposition gave mathematicians a whole new way to look at this problem.
Precisely. And that's the foundation for Wang and Wu's work. They build on this wave packet decomposition idea and really zero in on 2 major challenges.
Which are?
Understanding how these wave packets oscillate, and then figuring out their geometric interference.
Okay, hold on. Let's break those down one by one. When we talk about the oscillation of these wave packets, what are we really talking about?
Well, oscillation, it refers to the way these wave packets, fluctuate or change value as they travel through space. Think of it like ripples on the surface of water.
They have that up and down motion.
Exactly.
Yeah.
A complex but predictable pattern. And the challenge is figuring out how these oscillations from all these different wave packets interact with each other. Do they amplify? Do they cancel each other out? It's a delicate dance, and it's a huge part of what makes the restriction conjecture so tricky.
So we've got the oscillation of individual wave packets, and then we've got this geometric interference thing. What's that all about?
Okay, so picture each wave packet concentrated along a thin, tube-like region in space.
Okay.
Geometric interference, that's all about understanding how these tubes intersect and overlap.
So like a big jumble of straws, and we're trying to figure out which ones are crossing and where.
Perfect analogy. And guess what? The way these tubes intersect, it actually ties into another famous mathematical puzzle, the Kakeya conjecture.
The Kakeya conjecture. That's the one about finding the smallest area you need to rotate a needle 180 degrees, right? Always seemed like a simple geometry problem, but I'm guessing it's way more complicated than that.
It is. It's surprisingly deep. And it turns out it has some really profound connections to harmonic analysis and this restriction conjecture we're talking about.
Okay, so how does it connect to what we're talking about here?
Well, it provides us with tools to analyze the arrangement of these wave packet tubes and understand how they intersect.
So we've got these two big challenges. Figuring out the oscillation of individual wave packets, and then understanding how their geometric arrangement, linked to the Kakeya conjecture, impacts the bigger picture. So how do Wang and Wu even begin to approach this?
They use a really powerful tool called the refined decoupling theorem. It's a way to break down the problem into even smaller, more manageable pieces. We can actually isolate how each individual wave packet is contributing to the overall behavior of the extended function.
So it's like using a super powerful microscope to zoom in and study the interactions between these individual wave packets.
Exactly. And the refined decoupling theorem, it helps us quantify the impact of those interactions. It allows us to actually get a handle on that oscillation aspect of the problem.
Okay, but what about the geometric interference problem, all those wave packet tubes? Does this theorem help with that too?
It does. The refined decoupling theorem leads to a specific geometric problem, analyzing the arrangement of those thin tubes we were visualizing. The challenge is figuring out how many of them intersect a given region and how that number relates to the size of the extended function, which we measure using those LP norms.
So back to the straws, but now we're counting how many straws poke through a particular area.
Exactly.
And somehow we need to connect that back to the size of that extended function.
That's the heart of it. And this is where things get really interesting. See, those classic tools from the Kakeya conjecture, they're powerful, but they're not quite enough to solve this problem. They give us estimates that are too general. They can't quite capture all the subtleties of how these wave packet tubes are arranged.
So it's like trying to use a hammer to fix a watch. You need a more precise tool.
Exactly. So what Wang and Wu do is they introduce a key insight, something called 2n spacing. They came to this by using induction on scales, which is just a fancy way of saying they looked at the problem at different levels of detail. What they noticed was that the way these wave packets are distributed along their length, their shading, has a very specific 2n structure.
2n structure. What does that even mean in terms of those tubes?
Think of each tube as being really bright at both ends, kind of like those glow sticks you see at parties. And then it gets dimmer towards the middle. The 2n spacing, what it means is that this specific shading pattern actually limits how these tubes can be arranged in space. It adds another layer of constraints that the classic Kakeya tools weren't really taking advantage of.
So it's like we just discovered a secret code that tells us more about how these tubes fit together.
Clever. That's a great way to put it. So with this new 2n's information, Wang and Wu managed to prove a brand new inequality specifically designed to exploit this structure. They call it the planar 2n's Furstenberg inequality. And it gives them much more precise estimates, especially when dealing with the two-dimensional case.
Okay, so they invented a brand new mathematical tool just for this problem. And this helped them crack the restriction conjecture in 2 dimensions.
Exactly. The planar 2n's Furstenberg inequality gave them the leverage they needed to connect those geometric properties of the wave packet tubes with the analytical properties of the extended function, all measured with those LP norms. It's an elegant solution, really showcases the power of their new approach.
That's incredible, 2 dimensions down. But as we all know, higher dimensions are a whole other ballgame.
Oh, for sure.
So how do they handle those?
Well, they start by proposing a pretty bold conjecture. Essentially, it's a higher dimensional version of their 2n's Furstenberg inequality. They call it Conjecture 0.9 in the paper. And it basically says that this same relationship between tube density and intersection size, the one they proved in 2 dimensions, it should also hold true in higher dimensions, even though the geometry gets a lot more complicated.
Okay, so they're taking their two-dimensional blueprint and trying to build a skyscraper with it. Same basic principles, but way more complex.
Precisely. Now, they haven't been able to fully prove Conjecture 0.9 just yet, but they do provide some compelling evidence to support it and even offer strategies for tackling it.
Okay, what kind of evidence are we talking about here? And what are some of the hurdles they expect to encounter?
Well, for starters, they've been able to show that the conjecture holds true for certain specific geometric configurations in higher dimensions.
So they've tested it out on some smaller scale structures.
Exactly. And it works. They've also found some interesting connections to existing results in Furstenberg set theory, which lends even more support to their conjecture.
Wait, Furstenberg sets, those are those sets with all the weird dimensional properties and how they intersect lines, right? What's the connection there?
It turns out you can actually express Wang and Wu's conjecture 0.9 in the language of Furstenberg sets.
No way.
Yeah, which suggests there might be some deeper structure at play here and that maybe, just maybe, we can use tools from Furstenberg set theory to actually prove the conjecture.
It's like they found a secret passage between two completely different areas of math.
Exactly. But proving this conjecture in its entirety, that's a monumental task. One of the biggest obstacles is just the sheer complexity of higher dimensional geometry. Imagine trying to visualize and analyze those tube intersections in, say, 5 dimensions. It's incredibly difficult.
I can only imagine. What other challenges do they foresee?
Well, the tools we currently have for analyzing problems like the Kakeya conjecture, they might not be sophisticated enough to really capture the nuances of the 2n structure in higher dimensions.
We need to sharpen our tools.
Exactly. Or maybe even invent entirely new ones.
So they've really thrown down the gauntlet for the mathematical community. It's a call to push the boundaries.
They have, and to help guide future research, they've actually proposed some concrete stepping stones towards proving their conjecture, focusing on specific cases and approaches that could be really insightful.
Okay, tell me more about these stepping stones. What exactly are they proposing?
They've introduced 2 more conjectures, Conjecture 0.13 and Conjecture 0.15, and these are based on what are called Frost-Man axioms. These axioms give us a much more refined way to measure how these wave packet tubes are, how they're not concentrated, basically. They give us a clearer picture of their geometric properties.
So adding another layer of detail to our straw analogy, like now we can tell the difference between different arrangements of straws more easily.
Exactly. So Conjecture 0.13, that one focuses on 3 dimensions, and it uses something called the Frost-Man convex Wolf axiom, which helps us understand how tubes are arranged inside convex sets, a new angle to attack the problem. Then we have Conjecture 0.15, which expands on these ideas, but in even higher dimensions. It uses something called the Frost-Man polynomial Wolf axiom, which deals with how tubes are arranged within algebraic sets. So we're bringing in tools from both algebra and geometry here.
They're pulling out all the stops.
Yeah.
And are these conjectures, are they just stepping stones or are they important on their own?
That's the really cool part. They're both. These conjectures, while definitely helping us inch closer to proving that main conjecture, they're also really significant in their own right. They could help us make some serious progress on the Kakeya conjecture, which, as we've discussed, is a notoriously tough problem.
Wow, so it's like they're building a bridge between these two seemingly separate mathematical worlds.
Exactly, and who knows what amazing things we'll find once we cross that bridge.
Well, we've covered a lot of ground already in this first part of our deep dive. From historical context to the nitty-gritty of wave packet oscillation and geometric interference, we've really seen how Wang and Wu are tackling this challenge.
And the journey's not over yet.
Right. In the next part, we're going to take an even closer look at how they actually proved the 2n's Furstenberg inequality in 2 dimensions. It's a masterpiece of mathematical reasoning, and we'll break it down step by step. And then we'll explore their work in higher dimensions, see what progress they've made and what mysteries still remain.
Buckle up.
So stay tuned, everyone. We're about to go even deeper into the fascinating world of Fourier restriction theory.
Welcome back to our deep dive into Fourier restriction theory.
It's like we're on an expedition through the mathematical jungle.
That's a good way to put it.
So last time, we set the stage, explored the history, and got a handle on the key challenges Wang and Wu tackle in their paper.
Right, the oscillation, the geometric interference, all that good stuff.
Right. Now, I'm really excited to dig into the heart of their work. Let's start with their proof of the two ends Furstenberg inequality in the plane.
Yes, that was a real breakthrough.
It was. Can you remind us what that inequality is all about and why it's so important for solving the restriction conjecture?
Sure. Remember, the restriction conjecture, it's trying to establish a connection, a relationship between the size of a function that's defined on a curved surface and then the size of its extension, how it spreads out to the whole space. And we measure this size using those LP norms we talked about.
Right, the LP norms. Those are our mathematical rulers for measuring the magnitude of these functions.
Exactly. So the two ends Furstenberg inequality, this comes into play when we use that wave packet decomposition. We break down that extended function into smaller pieces, those wave packets, each one kind of concentrated along a thin tube-like region in space.
Okay, yeah, like those bundles of straws we were picturing before.
Precisely. And the two ends Furstenberg inequality, it gives us this powerful way to analyze how those tubes intersect and overlap, especially when they have that special two-end structure, bright at the ends, dimmer in the middle, like those glow sticks we talked about.
Okay, so it's a tool that helps us make sense of how those wave packet twos are arranged, taking into account that two ends property. And this tool was the key to unlocking the restriction conjecture in 2 dimensions.
It was. So let's take a look at their proof. See how they constructed this inequality. It's a really beautiful argument, blending geometry and combinatorics in a very clever way.
Lead the way. I'm all ears.
Okay, so they start by assuming we have a collection of these tube-like regions, and each one has that two ends shading pattern we talked about. What they want to do is prove an inequality that connects the density of these tubes, how many are packed into a given area, to the overall size of the region where they all intersect.
Okay, I'm following so far. So it's like figuring out how much space those glow sticks take up, knowing how bright they are and how they're laid out.
Exactly. And to get there, they analyze all these different scenarios, different ways these tubes can be arranged, and they apply some really clever counting arguments. They use the two ends property to get some crucial bounds along the way.
So they're like detectives, meticulously piecing together clues from the geometry of the problem, using that two ends information to their advantage.
A very good analogy. And one of the key steps is to divide the plane into a grid of smaller squares, and then they look at how many tubes intersect each square. Using that two ends property, they showed that the number of tubes hitting a square is actually controlled by the overall density of tubes in the plane.
So it's a game of tube gridlock, trying to cram as many tubes as you can to a limited space, but you have to follow the rules of the two ends constraint.
That's it. And after analyzing all these different scenarios, they finally arrive at their two ends Furstenberg inequality. This inequality gives us a precise mathematical relationship between the density of the tubes and the size of their intersection region.
And, as we discussed, this inequality is the bridge that lets them prove the restriction conjecture in 2 dimensions.
It is. It connects those geometric properties of the tubes to the analytical properties of the extended function, measured by those LP norms. It elegantly confirms the restriction conjecture in that 2-dimensional case.
Really impressive stuff. So they've conquered the 2-dimensional case using this new inequality. But what about higher dimensions? As we know, things get a lot more challenging there.
Absolutely. Higher dimensions are a whole other ballgame.
So how do they approach those more complex situations?
Well, they start by boldly proposing a conjecture, a higher dimensional generalization of their two ends Furstenberg inequality. Remember conjecture point 9?
Yeah, the one with those intriguing connections to Furstenberg sets.
That's the one. They're basically saying that the same fundamental relationship between tube density and intersection size, it should hold in higher dimensions, even though the geometry gets way more intricate.
It's like taking their 2-dimensional blueprint and trying to build a skyscraper. Same basic principles, but the scale and complexity are amplified.
Exactly. Now, they haven't fully proven conjecture point 9 yet, but they do provide some compelling evidence to support it and outline possible strategies for tackling it.
Okay, so what kind of evidence do they present? And what are some of the hurdles they anticipate in proving this conjecture?
Well, one piece of evidence comes from analyzing specific geometric configurations in higher dimensions. In these cases, they've shown that their conjecture actually holds true. These specific examples lend support to the broader idea.
So they've tested their blueprint on some smaller scale structures in higher dimensions, and it seems to be working.
Right. And they've also found connections to existing results in, you guessed it, Furstenberg's set theory. It further supports their conjecture. Remember those sets with their peculiar dimensional properties and how they intersect lines?
Yeah, those hidden passageways between different mathematical realms.
Well, they found a way to express conjecture point 9 using the language of Furstenberg sets. This suggests that there might be an even deeper structure at play here. Maybe we can use tools from Furstenberg set theory to finally prove the conjecture.
It's like they've discovered a new map, revealing hidden connections across the mathematical landscape.
Exactly. But proving this conjecture in all its generality is a monumental task. One of the biggest challenges is the sheer complexity of higher dimensional geometry. Visualizing those tube intersections in, say, 5 or 6 dimensions is incredibly difficult. It's like trying to untangle a massive ball of yarn where each strand represents a tube in a high-dimensional space.
Yeah, I can imagine that getting really messy.
It does. And the tools we currently have for analyzing problems like this, they might not be sophisticated enough to really capture the subtleties of that two-end structure in higher dimensions. We might need entirely new tools, or at least major refinements to our existing ones, to really make headway on this problem.
So it's a challenge to the mathematical community. We need better tools and deeper insights to crack this problem.
Absolutely. But even though a complete proof of their main conjecture remains elusive, Wang and Wu don't leave us empty-handed. They offer some concrete stepping stones, specific cases, and approaches that could give us valuable insights along the way.
Okay, tell me more about these stepping stones. What specific avenues did they suggest exploring?
They introduced 2 additional conjectures, Conjecture 0.13 and Conjecture 0.15. These are based on what are called Frost-Man axioms, which give us a much more precise way to quantify how those wave packet tubes are distributed, how they're spread out. It gives us a finer lens to analyze their geometry.
It's like upgrading our microscope to get an even clearer view of those straw arrangements.
Precisely. So Conjecture 0.13, that one focuses specifically on 3 dimensions and uses something called the Frost-Man-convex Wolf axiom. This axiom helps us understand how the tubes are arranged inside convex sets. It offers a fresh perspective on the problem. Then we have Conjecture 0.15, which takes these ideas to even higher dimensions. It uses the Frost-Man polynomial Wolf axiom, which deals with how tubes are arranged within algebraic sets. So now we're bringing in tools from both algebra and geometry.
They're really pulling out all the stops. And are these conjectures just stepping stones, or are they significant in their own right?
That's the amazing part. They're both. These conjectures are not only helpful in approaching their main conjecture, but they also have potential implications beyond the restriction conjecture. They could lead to advancements in the notoriously difficult Kakeya conjecture.
Wow, so they're building a bridge between these two seemingly distinct mathematical islands.
That's a great way to put it. And who knows what incredible discoveries await us on the other side. We've explored their work in 2 dimensions, their vision for higher dimensions, and in the final part of our deep dive, we'll examine the concrete progress they make in higher dimensions, even without fully proving their main conjecture. We'll unpack their improved restriction estimates and discuss the open questions that still beckon, giving you a glimpse into the future of this captivating field.
Welcome back to our deep dive. It's time to wrap up our exploration of Fourier restriction theory.
It's been quite a journey.
It really has. We've seen elegant proofs, those unexpected connections, and some pretty bold conjectures. But in this final part, I'm really curious about the concrete progress Wang and Wu made in those higher dimensions, even without fully proving their main conjecture.
It's remarkable what they were able to achieve. It really shows how powerful their approach is, even when dealing with those incredibly complex mathematical obstacles.
So tell me, what specific advances did they make? What new ground did they break in those higher dimensional spaces?
They significantly improved existing restriction estimates in higher dimensions. They actually refined the range of LP norms for which the restriction conjecture is known to hold.
Okay, and those LP norms, those are mathematical tools for measuring the size and smoothness of those functions, right?
Exactly. The restriction conjecture claims that for a certain range of these LP norms, the size of the extended function, the one that covers the whole space, can be controlled by the size of the original function on that curved surface. Wang and Wu, their work, they actually expanded that range. They pushed the boundaries of what we know, even without completely proving their main conjecture.
That's impressive. How do they manage to do that? Do they come up with completely new tools, or do they use existing techniques in a new way?
They did a bit of both, actually. They combined their own innovation, that planar 2-ends Furstenberg inequality we discussed earlier, and combined it with another 2-ends inequality developed by Katz and Tao back in 2002. By bringing these two ideas together, they were able to derive new estimates for how many wave packet tubes intersect specific regions in higher dimensions.
So it's like they took two powerful engines and combined them to create an even more powerful machine, and this led to those improved restriction estimates in higher dimensions.
Exactly. Their work really shows how adaptable and powerful the 2n's Furstenberg inequality is, even in those more complex higher dimensions. It's a testament to the power of combining creative thinking with existing knowledge.
Absolutely. Their research has definitely moved the needle on the restriction conjecture, but I imagine it also opened up new avenues for exploration. What are some of the open questions that remain? What are the next steps on this mathematical journey?
The most pressing question, of course, is whether their main conjecture, conjecture point 9, holds true in its entirety. Proving this conjecture would be a huge breakthrough. It would give mathematicians a powerful new tool to analyze wave packet interference in higher dimensions. It would be like reaching the summit of a mountain and seeing a vast new landscape of possibilities laid out before you.
What a fantastic image. Are there any other paths forward? Maybe something to do with those connections with Furstenberg sets?
Definitely. Exploring those connections further could lead to completely new techniques and ways of looking at the restriction conjecture. Remember how they were able to express conjecture point 9 in the language of Furstenberg sets? Well, digging deeper into that relationship could reveal hidden pathways and offer new tools for understanding the problem from a different angle.
It's amazing how this one research paper has sparked so many exciting possibilities and directions for future exploration.
It really is inspiring. Wang and Wu's work is a beacon, lighting the way for future mathematicians in their quest to understand this fascinating area of mathematics.
Well, we've reached the end of our deep dive into this groundbreaking research on the Fourier restriction conjecture. We've journeyed through elegant proofs, uncovered surprising connections, and contemplated bold conjectures.
We've seen how abstract mathematical ideas can have real-world applications and how the pursuit of mathematical knowledge is a never-ending adventure.
To our listeners, we encourage you to keep exploring, keep asking questions, and never lose your curiosity about the mathematical world. You never know what amazing discoveries you might stumble upon. Until next time, keep those minds sharp and keep exploring. Welcome back, everyone. Ready for another deep dive? Today, we're going to be tackling Fourier restriction theory.
Oh, nice.
Yes, specifically a paper that uses some really interesting techniques to try to make some progress on the restriction conjecture.
Right, the restriction conjecture. It's one of those classic problems that's been around forever, and it seems like every few years there's some new angle, some new tool that people try to use to attack it.
Yeah, and this paper claims to do just that. They use a combination of decoupling theorems and something called 2n's, Furstenberg inequalities.
Wow, okay. Those are pretty advanced tools, not exactly something you encounter in an introductory analysis course.
Definitely not. Even I had to do a bit of refreshing before diving into this one.
Yeah.
But that's part of the fun, right? Getting to learn about these cutting-edge techniques.
Absolutely. So what exactly are these decoupling theorems and Furstenberg inequalities, and how do they relate to the restriction conjecture?
Well, maybe the best place to start is with the restriction conjecture itself. I mean, we probably have some listeners who aren't familiar with it.
Right, good point. So the restriction conjecture, at its core, is asking a question about how much information we can glean about a function by looking at its Fourier transform, but only on a specific restricted set. It's kind of like trying to understand a whole object just by looking at its shadow.
Ah, okay, that's a good analogy. So, like, if you only see the shadow of a ball, you know it could be a ball, but it could also be something else entirely.
Exactly. And the restriction conjecture is trying to figure out under what conditions we can actually say, yeah, based on this restricted view, we can be pretty sure about certain properties of the original function.
Interesting. So where do these decoupling theorems and Furstenberg inequalities come into play?
Well, the authors of this paper use these tools to get very precise estimates on how much information we lose when we restrict the Fourier transform to certain sets. Decoupling theorems help us break down complex functions into simpler pieces, and Furstenberg inequalities provide bounds on how these pieces interact.
Okay, that makes sense. So they're kind of like a magnifying glass and a measuring tape for Fourier analysis, allowing us to zoom in and analyze the details of these functions in a very specific way.
That's a great way to put it. And the authors use these tools to make some pretty significant progress on a specific case of the restriction conjecture.
That's awesome. So should we jump right into the paper and see how they do it?
Let's do it. I'm curious to see how they actually apply these techniques.
All right, so the abstract on page 1 kind of lays out their game plan. They're specifically going after conjecture 0.1, which I'm assuming is their formal statement of the restriction conjecture.
Yeah, that sounds about right.
But then they mentioned something about Kakeya sets, which caught my eye. Those are those weird geometric objects where you're trying to rotate a needle in the smallest possible area, right? What on earth do those have to do with Fourier analysis?
It is a bit surprising, isn't it? The connection isn't immediately obvious, but it turns out that problems related to Kakeya sets and the restriction conjecture have this deep underlying structure in common, and progress in one area often leads to insights in the other.
Wow, that's fascinating. So even though they seem completely different on the surface, there's this hidden link between these geometric puzzles and the world of Fourier analysis.
Exactly. And that's part of what makes this paper so interesting. It's bringing together tools and ideas from these seemingly distant areas of mathematics to attack a really tough problem.
I love it when math does that. Okay, so let's dive into the introduction on pages 1 and 2. They start by introducing something called the extension operator, denoted by equation 0.1, which seems to be the heart of the problem.
Right, the extension operator. Think of it like this. You have some data on a curved surface, let's say,
Okay.
and you want to figure out how that data would naturally extend to the surrounding space. That's what the extension operator does. It takes a function defined on that surface and, well, extends it to the whole space.
Okay, I think I'm starting to get the picture. So the restriction conjecture is asking whether we can say something about the original function just based on its behavior on this restricted surface. And the extension operator is the tool we use to bridge that gap, so to speak.
Precisely.
All right, so the authors then give us a quick history lesson, mentioning some big names like Pfefferman, Thomas Stein, and Bourgain.
Yeah, those are some of the giants in the field. Their work laid the foundation for a lot of the modern approaches to the restriction conjecture.
And they also highlight a shift towards using wave packet decomposition to tackle the problem. Is this where things started to get really interesting?
Absolutely. Wave packet decomposition is a way of breaking down a function into smaller, localized pieces. Imagine taking a complicated wave and separating it into individual ripples.
Okay, so it's like taking apart a complex machine to understand how each component works.
That's a good analogy. By analyzing these individual wave packets, we can study the function's behavior in more detail, especially its oscillation and how these wave packets interfere with each other.
So it's like putting the function under a mathematical microscope.
Exactly. And this finer-grained understanding is crucial for tackling the restriction conjecture.
Awesome. So where do we go from here?
Well, on pages 2 and 3, the authors delve into the first set of tools they'll be using, focusing on this idea of decoupling.
Okay, decoupling. That sounds intriguing. What is that all about?
So remember those wave packets we talked about? Decoupling takes that idea a step further by separating the wave packets based on their frequencies or scales. Imagine you have a symphony orchestra playing a complex piece. Decoupling would be like isolating the sound of each instrument, allowing you to study their individual contributions.
So it's like a frequency filter for functions.
Exactly. And the authors use a specific result called the refined decoupling theorem, stated as theorem 0.3, to gain very precise control over how these wave packets interact at different scales.
And how does that help them with the restriction conjecture?
Well, by understanding how these wave packets behave, they can get better estimates on how the extension operator acts on functions with different frequency components. And that's crucial for understanding the restriction phenomenon.
Okay, that makes sense. They also mention these multiplicity factors, denoted by M and M,
Yeah.
and they link those to the Kakeya problem. How do those factors play into this whole thing?
Those factors, M and M, essentially measure how much the wave packets overlap. The more overlap, the higher the multiplicity. And this idea of overlap turns out to be deeply connected to the geometry of lines in those needle-rotating Kakeya sets.
So even though we're dealing with different mathematical objects, wave packets and needles, there's this underlying concept of overlap and arrangement that connects them.
Precisely. It's a subtle but powerful connection that the authors exploit.
Amazing. Okay, let's turn to pages 3 and 4, where they discuss problem 0.4, which looks at the interaction between balls and tubes. Is this diving further into that Kakeya connection?
It is. Problem point 4 is all about understanding how many tubes can hit the given ball. Imagine you have a bunch of balls and a bunch of tubes scattered in space. You want to figure out how many tubes can intersect each ball.
Okay, I can picture that. So where does the Kakeya problem fit in?
Well, the arrangement of those tubes is crucial. The authors introduce the Kakeya maximal inequality, which is a tool for estimating the number of tubes that can hit a ball. But they point out that this inequality isn't quite sharp enough for their purposes.
So they need a more refined tool.
Exactly. And that's where induction on scales comes in. It's a technique for breaking down the problem into smaller pieces at different scales, kind of like zooming in and out on the problem to get a better understanding of the geometry involved.
So it's like analyzing a complex machine by first taking apart its individual components and then seeing how they fit together at different levels of assembly.
Exactly. By analyzing the problem at different scales, they aim to get a more complete picture of how these tubes and balls interact.
Makes sense. Now let's move on to pages 4 and 5. This is where they shift gears a bit and start talking about tools for handling incidence problems. This is where the Furstenberg set estimate, stated as theorem 0.6, enters the picture.
Right, the Furstenberg set estimate. Now, this is where things get a little more abstract. Imagine each of those tubes we were talking about having a special subset of points highlighted within it.
Okay, so it's like each tube has a glowing section.
Yeah, you could think of it that way. The Furstenberg set estimate gives us a way to analyze how these glowing sections, or shadings as they're called, are distributed, and how they relate to the arrangement of the tubes themselves.
So we're adding another layer of complexity here. We're not just looking at tubes, but also at specific arrangements of points within those tubes.
Precisely. And the authors explain how this Furstenberg set estimate has led to some really nice progress in 2 dimensions. But they also point out a major challenge, extending this to higher dimensions.
What makes it so difficult in higher dimensions?
Well, it comes down to a spacing condition on those shadings. In 2 dimensions, it's easier to keep those highlighted points spread out in a specific way. But as you move to higher dimensions, it gets much harder to maintain that spacing while still covering the same amount of volume. Imagine trying to pack marbles into a box. In 2 dimensions, you can spread them out easily. But as you add more dimensions, it becomes harder and harder to keep them from clumping together while still filling the space.
Okay, yeah, I see how that would get tricky.
Yeah.
So the authors are basically trying to find a way to adapt this Furstenberg set estimate to higher dimensions where things get a lot more crowded.
Exactly. And that leads them to their key finding, the 2 ends Furstenberg inequality in the plane, which is theorem 0.7.
2 ends Furstenberg inequality. What's that all about?
Well, remember how those shadings are like highlighted sections within the tubes? The 2 ends part means we're specifically looking at situations where those highlighted points are concentrated towards the ends of the tubes.
Okay, so like a tube with glowing ends.
Precisely. And what's remarkable about this inequality is that it achieves similar effectiveness to the Furstenberg set estimate, but with weaker assumptions. It's like finding a shortcut, a more efficient way to analyze these complex arrangements.
That sounds promising. So how does this new inequality help them with the restriction conjecture?
They show that this inequality leads to improvements in estimates for the case of 3 dimensions. They even hint at its potential connections to the Kakeya conjecture, suggesting it could have implications beyond the restriction conjecture itself.
Wow, that's exciting. It sounds like they found a really powerful tool.
They have, and on pages 6 and 7, they start exploring these ideas in higher dimensions, laying out conjectures and evidence for what might be possible.
So they're pushing the boundaries even further.
Absolutely. They introduce a higher dimensional version of the 2 ends Furstenberg inequality as conjecture 0.9, and even go on to claim, in theorem 0.10, that proving this conjecture would actually imply the full restriction conjecture. It's a bold claim, but one that highlights the potential significance of their work.
That's incredible. It feels like we're on the cusp of some major breakthroughs here.
It certainly feels that way. And the authors continue their exploration on pages 7 and 8, where they propose alternative ways to extend the Furstenberg set concept to higher dimensions.
So they're not putting all their eggs in one basket?
Not at all. They're exploring multiple avenues, which is always a good sign in mathematics. They introduce conjectures 0.13 and 0.15, which offer different approaches to tackling the challenges we discussed earlier.
Different rules of the game for higher dimensions.
You got it. And they even connect these new conjectures back to the Kakeya conjecture, highlighting the deep connections between these seemingly disparate areas of mathematics.
This is incredible. It's like watching mathematicians build these elaborate frameworks and tools to tackle these incredibly complex problems. Before we get lost in the weeds, though, maybe we should take a step back and give our listeners a roadmap for what's to come. What can they expect? as we delve deeper into this paper?
Well, the authors are going to lay a solid foundation with a review of Fourier analysis in Section 4. Then, in Section 5, they bring all these tools and concepts together to prove their restriction estimates, showing the power of their approach.
It sounds like things are about to get pretty intense. Buckle up, everyone. We're about to dive into the heart of the mathematics in this groundbreaking paper.
All right, so Section 1, Preliminaries in Incidence Geometry. This is where they lay down the groundwork, all definitions and tools they'll need.
So it's kind of like setting the stage, getting all the props in place before the main act.
Exactly. They start with refining a set, which is basically picking a subset that still has certain properties you want.
Okay, so like sifting through a toolbox and keeping only the wrenches, because that's what you need for this particular job.
Yeah, I like that analogy. Then they talk about measuring the size of a set at a specific scale, using balls of a certain radius. They denote that with those vertical bars with a subscript.
Oh, right, I see that. So like E would be the minimum number of balls of radius needed to cover the whole set E.
Right on. And they use E to represent the actual union of those balls.
Okay, so E tells you how many balls you need, and E shows you the actual area they cover. Got it.
Then they bring up the concept of a DLSC set, which is a set that satisfies a specific inequality related to how many balls of different sizes you need to cover its intersection with other balls.
That sounds a bit tricky.
Yeah, it's a bit technical. It's basically a way to characterize how evenly spread out the points are within a set.
Okay, so like, are they clumped together or are they nicely dispersed?
Exactly. And then they prove lemma 1.4, which says that if you take a refinement of a C set, the resulting subset is still a S C set.
So even when you zoom in, the points are still well behaved in the same way. That's handy.
Right. And then they define a Katz-Tau SC set, another way to describe the distribution of points.
Which involves bounding the number of points within any ball of radius R.
I see that. Yep. And that bound depends on R and A. Lemma 1.6 says that if you refine a Katz-Tau set at a larger scale, it stays Katz-Tau, maybe with a different constant.
So those Katz-Tau sets are pretty robust then.
Yeah, they hold up well under refinement. Now, they introduced the idea of a uniform set, where the number of balls of a particular radius you need to cover it stays pretty much the same at different scales.
So the density doesn't change drastically as you zoom in or out. Kind of a nice property to have.
Absolutely. And lemma 1.8, the uniformization lemma, says that you can always find a refinement of any set that gives you this uniformity. Pretty powerful stuff.
It's like you can always tidy up any messy set and find a well-behaved subset. I like that.
Then they define a branching function, which measures how the number of balls needed to cover a set changes as you change the scale.
So it's like measuring how much a tree branches out as it grows taller.
Yeah, like that.
Yeah.
And lemma 1.10 lets you find a subset of branching functions that are all close to each other, which helps simplify things when you have a lot of sets to deal with.
Makes sense. Grouping similar things together always makes life easier.
Absolutely. Then they introduce lemma 1.11, which deals with Lipschitz functions.
Those are the ones that have a limited rate of change, right?
That's right. And this lemma helps break those functions down into smaller, more manageable pieces.
Kind of like approximating a curve with straight lines.
Exactly. They combine this with the previous ideas to give us proposition 1.12, which provides a framework for analyzing uniform sets at different scales.
So it's like having blueprints that let you understand the structure of a building at different levels of detail.
Precisely. And then they switch gears a bit and discuss point line duality in the plane.
Duality, that's where you can swap points and lines, right?
Yeah.
Like every point corresponds to a line and every line corresponds to a point.
Exactly. It's a neat way to switch perspectives and sometimes see things in a new light.
A different lens to view the same problem. Love it.
They extend this duality to relate families of balls and tubes, which helps translate between different geometric representations of the same concepts.
So it's like having multiple languages to describe the same object.
Exactly. Now, they bring in some language from the Kakeya conjecture, starting with the concept of shading. Remember those highlighted points within tubes?
Yeah, like the glowing sections we were talking about.
Right, that's the shading. They define ELY as the union of all the shadings in a family of lines L, basically combining all those glowing bits. And LX represents all the lines whose shading contains a specific point X.
Okay, so we're building up a way to analyze these complex arrangements of lines, tubes, and points.
Yep, and they define a dense shading, which means the shaded part of each tube takes up at least a fraction of its length. They also talk about refining sets of lines and shadings, which is like zooming in while keeping everything consistent.
Like looking at a smaller part of a map, but still understanding how it fits into the bigger picture.
Precisely. They define as the union of tubes of radius r covering the shading within a line L. Basically, they're approximating the shading with smaller tubes.
Like replacing a curve with a bunch of straight lines, a classic math move.
Exactly. And they define a specific scale, which depends on the shading density and another parameter. This scale marks a point where certain properties of the shading become important.
So it's like a tipping point where the shading's behavior changes.
Yeah, I like that. And this leads to the definition of a two ends shading, where the highlighted points are concentrated towards the ends of each tube.
Right, like those tubes with glowing ends we were picturing earlier.
Exactly. They prove a couple of lemmas about two ends shadings, lemmas 1.22 and 1.23. Then they define LT as the set of lines that intersect a particular 2T at an angle less than some given value.
So they're really getting specific about how these lines and tubes interact.
Yep, they're zeroing in on specific configurations, and then they define a set of lines as unparallel if their directions aren't too concentrated, which basically means they can't be too clustered together directionally.
So another kind of spacing condition, but this time for the lines themselves.
Exactly. And they wrap up this section with lemmas 1.26 and 1.27, which are about refining sets of lines and shadings while keeping certain properties intact.
Phew, that was a lot. It's like they've built this intricate and delicate structure, carefully defining each piece and making sure everything fits just right.
They have. And with all that groundwork laid, we're finally ready to dive into the heart of the paper and see how they use all these tools to prove their main theorems. All right, section 2. The two ends Furstenberg inequality in the plane. This is where the action starts.
Let's see what they've got.
Theorem 2.1, this is the big one here. It gives us an inequality connecting the size of the union of those two ends shadings. Remember those?
Yeah, the tubes with the glowing ends.
Right. It connects that size to the density of the shadings and a factor that measures how spread out the lines are. It's a key piece of the puzzle for tackling the restriction conjecture.
They mention using incidence estimates in the proof. What are those and how do they fit in?
Incidence estimates are basically ways to count how many times objects intersect.
Okay, so like how many times those tubes cross each other?
Yeah, something like that. Lemmas 2.3 and 2.4 give specific bounds on the number of distinct tubes that can show up in certain arrangements.
So they're using geometry to help them count.
Exactly. They also bring in Theorem 2.5 from another paper, which sets up a kind of either situation for sets of tubes and balls. It says either the number of balls is limited in a very specific way, or there's a scale where the balls are nicely uniform.
So no matter what, they get some useful information.
Right. And that helps them control the behavior of these sets. They combine that with lemma 2.4 to create proposition 2.7, which gives them 3 possible outcomes.
So they're narrowing down the possibilities, getting closer to their target.
Precisely. And they use corollary 2.8, which comes directly from that proposition, to further refine the conditions under which they can get a good bound on the size of that union of two ends shadings.
It's like a detective closing in on a suspect.
I like that analogy. Now they bring in this new concept, a DES-C set. It's similar to those SC sets from before, but now they're looking at a larger scale denoted by DE.
So zoom out a bit to get the bigger picture.
Yep. And lemma 2.10 assures us that even when they zoom out, these sets are still well behaved.
That's good. We don't want to lose any important details by changing our perspective.
Right. Now they get really clever and use their earlier two ends reduction to simplify theorem 2.1 into a more manageable statement, proposition 2.11.
Breaking down a big problem into smaller, easier chunks.
Exactly. Proposition 2.11 focuses on proving the inequality under some extra assumptions. And finally, they use that proposition as a stepping stone to prove the full Theorem 2.1, the two ends Furstenberg inequality in the plane.
Victory. But now on to higher dimensions. Section 3, this is where things get even more intense, right?
Oh yeah. They're after higher dimensional two ends Furstenberg inequalities now. The big guns for tackling the full restriction conjecture. They start with Theorem 0.8. Which gives an estimate for a specific case with a well-spaced condition. Think of it like a starting point.
They're not going to stop there.
Nope. They present a discrete lattice example that hints at a possible bound for a more general case. This example leads them to Conjecture 0.9, their proposed higher dimensional version of the two ends Furstenberg inequality.
And this conjecture, if they could prove it, would be a huge deal.
It would be. They state Theorem 0.10, which says that proving Conjecture 0.9 would actually prove the full restriction conjecture. It's a powerful statement.
It's amazing how these geometric ideas can have such a big impact on analysis. But they keep going, don't they?
They do. Conjectures 0.13 and 0.15 offer other ways to extend the Furstenberg set concept to higher dimensions.
More options.
More options. Remember those P-T, C-Q sets that got stuck in lower dimensions? These new conjectures try to get around that problem.
So new rules for a new game. Higher dimensional geometry.
You got it. They even connect these conjectures back to the Kakeya conjecture, showing just how interconnected all these ideas are. Section 4, they take a breath and review some Fourier analysis.
Back to basics for a moment.
Yeah, setting the stage for the final act.
The grand finale. Section 5, this is where they prove their restriction estimates. All that work comes together.
Yep. Theorem 0.17, this is the culmination. An improvement on the restriction conjecture for general dimensions using their techniques.
Wow, that's quite an accomplishment. They do say it's not optimal, but it's still a big step forward. They've opened up a whole new way of thinking about the restriction conjecture.
Absolutely. This paper is a testament to how powerful and beautiful math can be. They brought together geometry and analysis to make real progress on a really tough problem.
Well, that was a wild ride. From basic definitions to intricate geometry to mind-bending analysis. And to think, it all started with the simple idea of restricting a function.
It just goes to show that even the simplest ideas can lead to incredibly rich and complex mathematics.
Absolutely. And that's what makes this field so exciting. There's always more to discover, more connections to make, and more problems to solve. So to our listeners, keep exploring, keep questioning, and keep diving deep into the world of mathematics. All right, everyone, get ready for a deep dive today. We're going deep into the world of advanced mathematics, specifically the Fourier restriction conjecture. And we've got some surprising connections to concepts like Kakeya sets.
Oh, absolutely, yeah.
It's going to be a fascinating ride, so buckle up. We're dissecting a research paper titled Restriction Estimates Using Decoupling Theorems and 2n's Furstenberg Inequalities.
It's a paper that really tries to solve this puzzle that's been around for, well, decades.
Yeah.
And the approach it takes is really clever.
Absolutely. So, to kick things off, the paper dives right into defining this thing called the Fourier extension operator.
Okay.
They use this notation, E sub s, and here's how they define it. E sub s of x equals the integral over s of e to the power of x dot s times f of to sub s of s.
So what's going on here? Can you kind of unpack this for us?
Sure. Imagine you've got a function, f, right? And it's defined only on a smooth hypersurface, s, in some higher dimensional space.
You can think of this hypersurface as well, kind of like a curved membrane, vibrating in this space. This Fourier extension operator, what it does is it takes that function, which is only defined on this membrane, and extends it to the whole space, kind of like letting those vibrations just spread out, like ripples.
Oh, okay. So taking a localized signal and then letting it ripple outwards?
Exactly.
That's a cool visual.
Yeah, and the way it does this, it's through those oscillating exponential terms you see in the integral.
Right.
Those create these wave-like patterns, propagating outwards from that surface.
Okay.
Now, the real challenge is understanding how these extended functions behave, especially how big they can get as they spread out.
Right.
That's where those LP norms come into play.
Okay, got it. And this leads us to conjecture point 1, which they kind of present as the central problem, right?
Right.
And it states that if S is a compact C2 hypersurface with a strictly positive second fundamental form, then for P greater than 2n over n minus 1, the LP norm of E sub S of F is less than or equal to C sub P times the LP norm of F. With respect to the surface measure, de sub S. So what does this conjecture actually mean? Like in a practical sense, what are we trying to get at here?
Well, this conjecture, it's really trying to nail down exactly when we have good control over the size or maybe the growth of these extended functions we were talking about.
Okay.
You see that condition on P, right? Where it needs to be greater than 2n over n minus 1.
Right.
That's kind of like a threshold.
Okay.
Beyond that threshold, we can actually predict how much the function can grow as it spreads out.
So it's like setting a speed limit for the ripples, kind of.
Yeah, that's a good analogy.
Okay, I like that.
And the authors, they actually managed to prove a specific case of this conjecture in theorem 0.2.
Okay.
It says that the conjecture holds true when n equals 3 and p is greater than 22 over 7.
Oh, so they've actually proven it. At least in three-dimensional space and for certain p-values.
Right.
We can actually say, hey, we know how much these functions can grow. That's pretty cool.
Yeah.
Now, to tackle this whole problem, they dig into a bit of mathematical history, mentioning some of the pioneers like Pfefferman and Tomas.
Absolutely. Pfefferman, he was the first to really crack this problem, but only in the two-dimensional case.
Okay, so the first one to get it.
Yeah. And then Tomas, he took those ideas and extended them to higher dimensions. He used some, ingenious techniques, really, involving the Fourier transform.
Okay.
His work led to what we now call the Stein-Tomas estimate.
Okay.
It gives us an upper bound on the growth of those extended functions,
Right.
but it only works for specific p-values.
Okay, so we've got some groundwork, but there are limitations.
Right.
And that's where this guy Burgang comes into the picture.
Right. Yes.
With this game-changing idea, wave packet decomposition.
Yeah. It was a real breakthrough, his approach. Instead of trying to understand the entire extended function all at once, he breaks it down into smaller wave-like components. We call them wave packets.
Okay.
Think of it like taking a complex musical chord and separating it out into its individual notes.
Okay.
You're analyzing the individual frequencies that make up the whole signal.
Got it.
Each wave packet is localized,
Okay.
both in space and frequency.
Okay.
Makes it much easier to analyze.
Makes sense.
By understanding these individual components, we can gain insights into how the whole extended function behaves.
Okay, so now that we have this decomposition in hand, what's next?
Well, now we need to focus on two key aspects. How much these wave packets oscillate and how they overlap with each other in space.
Got it. So that brings us to the refined decoupling theorem.
Yay.
Theorem point 3. So can you explain what this decoupling does?
Sure. Decoupling is this powerful technique. It helps us control the energy of these wave packets within certain regions of space.
Yeah.
It involves bounding how much those wave packets overlap, and it introduces this concept called a multiplicity factor,
Okay.
denoted by M. Think of it this way. If you've got a bunch of waves crashing together,
Okay.
the multiplicity factor is measuring how many waves are actually colliding at any given point.
Okay, so the lower the multiplicity factor, the less interference there is between the wave packets.
Exactly. The refined decoupling theorem gives us a way to control this multiplicity factor.
Oh, okay.
And that's crucial for understanding the overall behavior of the function.
Got it.
And here's where things get really interesting. These multiplicity factors, they're really closely linked to geometric arrangements of tubes.
Okay, so now we're bringing in the geometry.
Yeah. This is where those Kakeya-type problems come into play.
That's fascinating how a problem about extending functions can lead us to these geometric puzzles. What's the connection?
Well, the connection is in the supports of those wave packets. Each wave packet essentially occupies a tube-like region in space. And these tubes, kind of like the lines in those Kakeya sets you mentioned earlier,
Yeah.
they can be arranged in all these intricate ways that occupy surprisingly little space.
Okay.
The multiplicity factor measures how much these tubes overlap.
Oh.
So understanding their arrangement becomes crucial for controlling the whole function's behavior.
Got it. I see how those pieces fit together. Now, the paper points out this crucial observation in equation point 5.
Right.
It links the L2 norm of the extended function to a parameter, lambda. What's lambda doing here?
So this parameter, lambda, it's measuring how many small balls intersect each of those tubes.
Okay.
The smaller the lambda, the tighter the bound on the L2 norm of that extended function.
Right.
Which means we have better control over its growth.
So the goal is to make lambda as small as possible.
Exactly.
Okay.
And this leads us to problem point 4, which is all about finding an upper bound for that multiplicity factor, m.
Okay.
If we can control m, we can control lambda.
Right.
And then we can control the function's growth.
Got it.
Yeah.
So problem point 4 is like a key stepping stone to proving the restriction conjecture.
That's right.
Now, to try to tackle this problem, they explore using this thing called the Kakeya maximal inequality, but it seems to run into some limitations, right?
Yes, the Kakeya maximal inequality, it gives us a potential bound.
Okay.
It's shown in equation point 6, but it's not quite tight enough. It's like trying to fit a square peg into a round hole.
It almost works.
Almost, but there's a little gap.
There's a gap, but they don't give up.
Right.
They introduce this this method of induction on scales. What is that?
Okay, so it's a technique where you break down the problem into different scales. Think of it like zooming in and out on a map.
Okay.
You start by looking at the big picture, then you zoom in to see details, then you zoom in further, and so on.
Right.
At each level, you try to figure out how those tubes are arranged.
So You're analyzing the problem at different levels of detail.
Exactly. And this technique, it leads to a really interesting split. Either we get the desired result through this multi-scale analysis,
Okay.
or we discover some additional geometric information about how those tubes are intersecting with those small balls.
Okay. And that additional geometric information, is that what leads to the two ends assumption?
Yes, exactly. The two ends assumption basically says that the points where those tubes intercept the balls, they're concentrated on opposite ends of the tubes, like they're entering and exiting the ball from opposite sides.
So it's straight on the geometry of those intersections. And this assumption, it has a huge impact on the estimates, right?
It does. In the case of R, it drastically improves the estimate we see in equation 0.7. It's like finding a key that unlocks a hidden door.
Okay, wow. Now the paper shifts gears a bit. It starts talking about incidence problems in the plane.
Right.
They bring in the Furstenberg set estimate,
Right.
theorem 0.6. What's that all about?
Okay, so theorem 0.6, it gives us a powerful tool to understand how lines and balls intersect in the plane. But it depends on a pretty strong spacing assumption.
Okay.
Requires those intersection points to be spread out in a very specific way.
And that's not really the situation we have with the two ends assumption.
You're right, the two ends condition is a bit more relaxed.
Yeah.
But here's where things get really surprising.
Okay.
Theorem 0.7, which the authors call the two ends Furstenberg inequality, shows that even with this weaker two ends condition, we can still get the bound we need in the plane.
Wait, so even though the stricter spacing requirement of the original Furstenberg set estimate doesn't hold, we can still get the same level of control using this two ends inequality. That's pretty remarkable. What are the implications of that?
Well, this result has a huge consequence.
Okay.
It lets us prove the restriction conjecture in our raw using decoupling techniques.
Wait, so by combining decoupling with this two ends Furstenberg inequality, we've cracked the restriction conjecture in the plane. That's huge.
It is, and it opens up exciting possibilities for higher dimensions. The authors propose conjecture 0.9. It basically generalizes this two ends Furstenberg inequality to higher dimensions.
Okay.
If it's true, it would actually imply the full restriction conjecture, as stated in theorem 0.10.
So this two ends Furstenberg inequality could be the key to unlocking the whole puzzle. And they even provide a discrete example, right?
Yes, they do.
To support this conjecture in higher dimensions.
They look at a configuration of lattice points and lines. It shows the behavior we want, suggesting that conjecture 0.9 might be on the right track.
Okay, so we've got this really tantalizing conjecture. We've seen how it could solve the restriction problem. But then the paper introduces these new concepts, the T-Frossman convex Wolf axiom and the T-Frossman polynomial Wolf axiom.
Yeah,
These seem pretty abstract.
they are, but they're really important for understanding how those tubes are distributed in space, particularly in higher dimensions.
Yep.
The T-Frossman convex Wolf axiom, essentially, it measures how densely those tubes can be packed within convex sets.
So it's a way to quantify how much they're clumped together or spread out.
Exactly. And this leads to conjecture 0.13. It suggests a lower bound for the size of the set formed by the union of all those tubes, each one with its own shading.
Okay.
It's like trying to understand the volume this complex configuration of tubes and their intersections takes up.
And for dimensions 4 and higher, they need the even stronger T-Frossman polynomial Wolf axiom,
Yes.
which uses, what are they called, semi-algebraic sets instead of convex sets? Why the upgrade?
Well, in higher dimensions, things get much more complex.
Okay.
Convex sets aren't really enough to capture all the nuances of how those tubes can be arranged.
Okay.
Semi-algebraic sets, they offer a more refined framework to analyze these higher dimensional configurations.
Got it. So we're upgrading our toolbox
Exactly.
to handle this increased complexity. And this stronger axiom leads to conjecture 0.15,
Right.
which generalizes conjecture 0.13 to higher dimensions.
Yes, exactly. Conjecture 0.15 basically proposes a potential lower bound for the, well, let's call it the volume that those tubes and their shadings occupy in higher dimensions.
Okay, I think I'm starting to see the big picture here.
Good.
These axioms and conjectures, they're laying the groundwork for understanding the geometry of those tubes.
They are.
But the paper doesn't just stop at conjectures. They actually prove some concrete results, right?
Yes, they do.
In higher dimensions.
Theorem 0.17 gives us a concrete result for the restriction conjecture in higher dimensions. It improves on what we knew before.
Okay.
It might not be the complete solution, but it's a big step forward.
So even though the full conjecture is still out there, they made some serious progress
They did.
using this combination of decoupling and 2n's Furstenberg inequalities. That's impressive.
It is. It shows the power of these techniques for these tough problems in harmonic analysis and geometric measure theory.
Well, this has been a whirlwind tour of some really advanced math. I'm feeling a bit overwhelmed, but in a good way.
It's a lot to take in, but that's what's so exciting about pushing the boundaries of mathematics. There's always more to discover.
Absolutely. So should we start breaking down those definitions now?
Let's do it.
Okay, let's get into it.
Absolutely. Let's unpack these definitions, I guess.
Yeah?
They really form the foundation for, all those intricate arguments they're going to make later.
Sounds good. So first up is refinement, as defined in section 1.
Okay.
They say, for two finite sets E and F, subset of R to the power n, we say E is a less than or equal to C refinement of F, if E is a subset of F, and the cardinality of E is less than or equal to C times the cardinality of F. We say E is greater than or equal to C refinement of F, or simply a refinement of F, if E is a subset of F, and the cardinality of E is greater than or equal to C times the cardinality of F. What's the intuition behind this definition?
So refinement, it's all about creating a subset of a larger set, but you still want to keep a significant chunk of its elements.
Right.
Think of it as a controlled downsizing. The parameter C, it tells you how much you're trimming down the set. If C is 1, then E and F, they have the same number of elements. If C is less than 1, then you're taking a smaller piece of F. And if C is greater than 1, well, you're essentially allowing E to be bigger than F, as long as it's still a subset.
I see. So it's like creating smaller or sometimes larger versions of a set, but you still have some control over the relative size.
Right.
What's the purpose of introducing this concept? Why is it important?
Well, it's especially useful when you're dealing with coverings. Imagine you have a region, and it's covered by, a ton of sets.
Okay.
Refinement lets you find a smaller collection that still covers the same area.
Okay.
Could simplify things a lot.
Right. It makes things more manageable.
Exactly.
Okay. That makes sense. Now let's move on to delta SC sets.
Okay.
They sound a bit more technical.
A little bit, yeah.
The definition they give is, let delta be an element of 0, 1, 1, a small number. For S, an element of 0 n times S, a non-empty set, subset of R to the power of n, is called a delta SC set, or simply a delta S set. If C is not important in the context, if the cardinality of E intersected with the ball centered at X with radius R, with respect to delta, is less than or equal to C times R to the power S times the cardinality of E with respect to delta for all X and R to the power of n and R as an element of delta, 1m.
So what are we talking about here? What's the idea behind this definition?
Okay, so this definition, it might look a bit scary,
Yeah.
but it's really capturing this idea of dimensionality, but for sets at a particular scale, which we call delta.
So we're looking at the set at a certain zoom level, basically.
Exactly. Delta is like the resolution of our, well, you could say our mathematical microscope. Now, a delta SC set, it kind of behaves like an S-dimensional object when you view it at this resolution, delta.
Okay.
The definition is saying that if you pick any ball with radius Rs.
Right. And you count how many points from your set E fall inside that ball, that number is going to scale like R to the powers.
Can you give me an example? I'm trying to picture this.
Sure. Imagine a curved line in a plane. Now, if you zoom in really close, it starts to look like a straight line, right? Like a one-dimensional object.
Right.
But if you zoom out, that curve might, wind around and occupy a good chunk of a two-dimensional region.
Right. Okay.
So this definition, it lets us actually quantify how much space a set is taking up at these different zoom levels.
So it's like saying a coastline can look one-dimensional if you're up close, but from a distance, it's actually two-dimensional.
Exactly. A delta SC set, it helps us make sense of this this multi-scale behavior.
Okay, that's a helpful way to think about it. Now, they also introduced the cat's tau delta SC set,
Right.
which seems pretty similar, but specifically for finite sets.
Right.
Their definition. Let delta, an element of 0, 1, be a small number. For S, an element of 0n times S. A finite set, E subset of R to the power of n, is called a cat's tau, delta SC set. Or simply a cat's tau, delta S set. If C is not important in the context, if the cardinality of E intersected with a ball centered at X with radius R is less than or equal to C times R delta to the power S for all X and R to the power of n and R, an element of delta 1. What's the key difference here? Why introduce this separate definition?
So you're right. It's a similar idea, but now we're focusing on finite sets.
Okay.
So instead of looking at the cardinality of the whole set, we're looking at how many points from this finite set E are inside a ball of radius R.
Right, okay.
And the definition, it says that this number is going to scale like R delta to the powers. Again, reflecting some notion of dimensionality at this scale delta, but specific to these finite sets.
So both are trying to capture how much space a set occupies at different scales.
Yep.
But one's tailored for finite sets. The
Right.
other works more generally.
Exactly.
Okay. And just to remind myself, these concepts are building blocks for understanding the more complex stuff, like with those tubes and the restriction and Kakeya problems.
Exactly. You got it.
Okay, good. Now they define uniform sets as, let delta be an element of 0, 1, be a small number, let m equal the absolute value of the logarithm of delta, and let rho sub j equal m to the power of negative j, where j equals 1, 2, and so on, until the floor of logarithm base m of delta inverse, which we denote as n. Given E union of delta balls in R to the power of n, we say E is uniform with error C if the cardinality of E intersected with D sub rho sub j with respect to rho sub j are the same up to a multiple C for all D sub rho sub j subset of E sub rho sub j. When C is not important in the context, we say E is uniform. This one feels a bit more intuitive, I guess.
Yeah, I think so. This definition is about making sure the set is, well, uniformly distributed at different scales. So
Okay.
think of it like we're covering this set, E, with balls of different sizes, right? Denoted by rho sub j. If the number of balls you need to cover each part of E is roughly the same at each scale up to a factor of C,
Okay.
then we say the set is uniform.
So it's like saying the set doesn't have any regions that are overly dense or overly sparse at these different scales.
Precisely.
It's spread out evenly.
Evenly, yes. And this concept, this uniformity, it allows us to study the set's properties without getting bogged down by those local variations. We can look at the average behavior across all the scales.
Okay, well, uniformity is a way to simplify the analysis. Makes sense.
Right.
Now, the next definition introduces this branching function. It sounds interesting.
Yeah.
Definition 1.9 says, let delta be an element of 0, 1, and let m equal the absolute value of the logarithm of delta. Let rho sub j equal m to the power of negative j, j equals 1, 2, up to the floor of logarithm base m of delta inverse, which we denote as n. Let E, a subset of R to the power of n, be a union of delta balls that is uniform. Define a branching function beta sub E from 0n to 0n as beta sub E of j equals logarithm of the cardinality of E with respect to rho sub j, divided by the absolute value of the logarithm of delta, where j is between 0 and n, and interpolate linearly between beta sub E of j and beta sub E of j plus 1. So can you unpack this one for me? What's going on with this branching function?
Okay, so this branching function, beta sub E, it basically tells us how the size of this uniform set E changes as we change the scale, the zoom level.
Okay.
Essentially, it's calculating the logarithm of the number of balls needed to cover E at different scales.
So it's like a growth rate for the set as you zoom in and out.
Exactly. And that growth rate can actually tell you something about the set's dimensionality. Linear growth might be like a line, quadratic growth, maybe it's a plane, things like that.
So it's like quantifying that dimensionality concept that we were talking about earlier.
You got it.
Okay.
Yeah.
So the branching function is really about understanding the multi-scale structure of sets.
Right.
Which makes sense. It's important for these restriction and Kakeya problems.
Right.
Okay, next up is point line duality.
Okay.
Which sounds like it could be visual.
It is, yeah.
In definition 1.13, they state, suppose L is a family of non-horizontal lines in R squared. Then each L in L can be parameterized as L of AB, which equals A0 plus R times B1. Let P be the set of AB such that L of AB is an L, which is a subset of R squared. Therefore, the map F from points in R squared to non-horizontal lines in R squared, where F of AB equals L of AB is 1 to 1. Moreover, if P is contained in a compact set, then F and its inverse, F inverse, are both Lipschitz. The map F and its inverse, F inverse, are both referred to as point line duality. What's this duality all about?
So point line duality, it's this cool trick. It lets you change problems about lines into problems about points and vice versa.
You can flip between the two.
Yeah. In the plane, every point A, B corresponds to a unique non-horizontal line. Equation y equals bx plus a,
Right.
and the other way around. Every line can be represented by a point. What's really neat is that this duality, it preserves incidences. So if a point lies on a line, then the point corresponding to that line, it lies on the line corresponding to that point.
Okay, that's a really neat trick. I can see how that would be super useful when you're trying to analyze intersections of lines.
Yeah.
And they even extend this duality to delta balls and delta times 1 tubes.
They do,
They
yeah.
state, we can extend the point line duality to a family of delta balls in the unit ball and a family of delta times 1 tubes contained in the unit ball by noting the following. If P, which is a subset of the ball centered at 0 with radius 1, is a delta ball, and T is a delta times 1 tube contained in the unit ball that is quantitatively transverse to the x-axis, then P intersected with T is non-empty if and only if F inverse of T intersected with F of P is non-empty. Here, F inverse of T is the union of points F inverse of L, where L intersected with T is a subset of T. Thus, a family of delta times 1 tubes can be identified as a family of delta balls, and we can make the following definition. So we're essentially mapping those tubes and balls to points and lines in another space, but their intersection properties are preserved.
Right.
So we can study those intersections by looking at the corresponding points and lines.
Exactly. It's a powerful way to, translate these geometric problems into something, well, potentially simpler.
Okay, we've covered a lot of definitions already. Refinement, delta, SC sets, Katz tau sets, uniform sets, branching functions, and point line duality. Is that everything?
Almost. We still need to talk about shading, E sub L, Y, lambda density, and 2n's.
Okay.
These are all crucial for setting up the specific geometric framework they're going to use to tackle these restriction and Kakeya conjectures.
Got it. Let's dive into those then, starting with shading. What does that even mean here?
So shading basically allows you to put weights on different parts of lines or tubes. It's like highlighting the segments of those geometric objects that are most relevant to the problem.
So instead of considering the whole line or tube, we're zooming in on specific parts.
Yeah, exactly. We're focusing on the segments that matter most. Then there's lambda density. It quantifies how densely these shadings are distributed within the lines or tubes.
Okay, so it measures how much stuff is packed into those highlighted segments. And 2n's, I'm guessing that refers to the condition we talked about earlier, where the intersection points are at opposite ends of those tubes.
You got it. The 2n's condition forces a specific geometric constraint on how those shadings are arranged.
Right. And we saw earlier how powerful that seemingly simple condition can be.
We did.
Led to some big improvements in those estimates.
Yeah, it all comes down to finding the right way to look at things, the right geometric framework, the right tools to analyze these intricate configurations.
Okay. Well, this has definitely been a deep dive into definitions. I'm starting to feel like I'm getting a much better grasp of things now.
Good.
Ready to move on to section 2.
Let's do it.
Okay, section 2. Excited to see how they use all those definitions now.
So this section, they're focused on proving the 2n's Furstenberg inequality in the plane. It's stated as theorem 2.1, and it's really important for their whole approach to the restriction conjecture.
All right, let's hear it. What's the theorem say?
Okay, so theorem 2.1 states, let delta be an element of 0, 1. Let Ly sub delta be a set of one parallel delta-separated lines in R squared with an epsilon sub 1, epsilon sub 2, 2n's, lambda dense shading. Then, for any epsilon greater than 0, the cardinality of E sub L is greater than or equal to C sub epsilon times delta to the power of epsilon times delta to the power of epsilon sub 1 divided by 2 times lambda to the power of 12 times the sum over all L and L of the cardinality of Y of L.
Whoa. Okay, that's a lot. Can you break it down a little?
Sure. So we've got a collection of lines, L, in the plane. They're parallel, and they're spaced apart by delta.
Okay.
Each line has a what they call a shading. You can think of it as a highlighted segment.
Right.
These shadings, they're lambda dense, meaning they're packed together with a certain density. What the theorem is saying is that the size of this set E sub L, which is formed by taking all those shaded segments together, it's bounded from below by a bunch of factors that are related to the density of the shading, that's lambda, the spacing between the lines, delta, and the length of those shaded segments, which is captured by those epsilon parameters.
So it's like giving us a lower bound on the total area that those shaded segments cover.
Exactly.
Taking into account how densely they're packed and how they're arranged on the lines.
You got it. And this bound, it uses the 2n's condition, meaning those shadings, they're concentrated at opposite ends of the lines.
Okay.
Now, the proof of this theorem, it's pretty intricate.
I bet.
They use a mix of multi-scale analysis, dyadic pigeonholing, and that point line duality we talked about.
So they're pulling out all the stops. Can you give me an idea how the proof actually works?
Sure. They start by breaking the problem down into smaller pieces, looking at the lines at different scales. They use this thing called dyadic pigeonholing to group together lines that have similar properties.
Okay.
Then they apply the point-line duality
Okay.
to transform the problem about lines into a problem about points.
Right. It makes it easier to analyze.
Exactly.
Classic divide and conquer.
Yeah.
Break it down, solve the smaller parts, put it all back together.
Precisely. It's a really nice example of, well, how powerful these tools can be when you use them together.
All right. So now section 3 seems to be kind of a bridge between those planar results and higher dimensions.
Yes.
They introduce the higher dimensional two ends Furstenberg inequalities. Why are these higher dimensional versions important?
Well, those higher dimensional inequalities, they're key to proving the main theorems about the restriction conjecture.
Okay.
They start with lemma 3.1. It gives an estimate for that multiplicity factor in 3 dimensions using the two ends assumption.
Oh, so they're taking that geometric insight about the tube intersections and bringing it up to higher dimensions.
Precisely.
Yeah.
And this lemma is crucial for proving theorem point 2.
Right.
Which establishes the restriction conjecture for n equals 3 and p greater than 227. Remember that one?
Yes, I do.
They also make a clear connection between this result and the Kakeya conjecture,
Okay.
highlighting that, that beautiful relationship between the exponent p in the restriction conjecture and the exponent in the Kakeya conjecture.
It's amazing how connected these problems are.
It really is. Progress in one often helps with the other. Now, Section 4 kind of takes a step back, reviews some essential stuff from Fourier analysis,
Okay.
like a refresher course,
Right.
on the basic tools they're going to use in the next section.
Okay, setting the stage. So section 5, that's where they prove the restriction estimates.
That's it. This is where it all comes together.
I'm ready to see how it all works.
So they start by proving proposition 5.1.
Good.
Establishes a restriction estimate in dimensions under some specific geometric conditions.
Okay.
This proposition relies heavily on the refined decoupling theorem.
Right. And those higher dimensional two ends Furstenberg inequalities they developed earlier. So they're pulling out all the big guns now.
Exactly. They're attacking the restriction conjecture from all angles.
I like it.
And that proposition, it's then used to prove theorem 0.17, their final result for the restriction conjecture in these higher dimensions.
And this is the theorem that improves on the previous findings, provides that concrete range of p-values where the conjecture holds.
You got it. It might not be the complete answer to the restriction conjecture,
Right.
but it's a major step forward. Shows how powerful their approach can be.
Well, this has been quite the deep dive. We explored this Fourier restriction conjecture, found these unexpected links to the Kakeya conjecture, and saw how well sophisticated these mathematical tools really are.
It's been great exploring all this with you.
Yeah, it has. Who knows? Maybe this paper will inspire someone to finally solve the whole restriction conjecture.
I'm sure it will. If anyone listening is as interested in this as we are, I definitely recommend checking out the full paper.
Yeah, absolutely. There's so much more to discover.
Until next time, keep exploring, keep asking those questions, keep diving deep.
All right, so we're diving into this paper you sent over restriction estimates using decoupling theorems and two ends Furstenberg inequalities. It's by Wang and Shukun Wu and tackles the Fourier restriction conjecture. I got to say, though, those tools they use sound pretty intimidating. Decoupling theorems and two ends Furstenberg inequalities.
Yeah, it's a pretty clever combo for sure, going after a problem that's had mathematicians scratching their heads for ages, you know? This Fourier restriction conjecture, as they laid out in conjecture 0.1, it gets into how a function behaves on this smooth hypersurface, and then how that affects its extension out into, like, the whole Euclidean space.
So it's about, like, if you've got this function doing its thing on a curved surface, the conjecture is trying to figure out how that impacts the function in the bigger picture. Kind of like, I don't know, like if you had a ripple on a pond, how that affects all the water moving around.
That's actually a pretty good way to think about it, yeah. What they're trying to do is put a limit on how big the extended function can get based on how the original function is acting on that hypersurface. You can see it in equation 0.2 in the paper, how they connect that L sub norm of the extended function. They write it as E sub f. And then they link that to the L sub norm of the original function f on the hypersurface S.
They mention Pfefferman, right? Like he nailed it in 2 dimensions, but Going beyond that into higher dimensions seems to be where things get really tricky.
Exactly. Pfefferman's work was a huge breakthrough, don't get me wrong, but taking those results and making them work in higher dimensions, man, that's a whole other beast. It gets so much more complex once you leave flat land behind.
And that's where these decoupling theorems step in, right? It sounds like they could untangle, well, just about anything.
That's a good way to picture it. What decoupling does is it lets us take a function and break it down into smaller chunks. Then we can see how all those little pieces interact with each other. Theorem point 3 is the big one here, the refined decoupling theorem. It's a game changer. It basically takes this problem about norms, which is all analytical and stuff, and turns it into a geometry problem. It's all about how these tubes are arranged in space.
So instead of going straight at the function's behavior, we're looking at where it's concentrated in these tubes and how those tubes are laid out.
Exactly. The theorem shows how the size of that extended function is tied to how many of these tubes are overlapping. And that shift to a geometric view is what lets us use tools like 2n's Furstenberg inequalities.
Okay, now for the big question. What in the world are 2n's Furstenberg inequalities, and how do they actually help us?
So picture these tubes, right?
Right.
What the 2n's condition basically says is that when those tubes intersect a region, the points where that happens are all bunched up near the two ends of each tube. It seems simple, just a geometric quirk, but it has some wild consequences.
So all the action is happening at the tips of the tubes. Sounds almost too easy.
I know, right? But it's a powerful idea. By using that 2n spacing, we can get some surprisingly strong estimates for how many tubes are cutting through a specific ball, like they show in theorem point 7. That's what sets the stage for them to attack the restriction conjecture in higher dimensions.
But I'm guessing it doesn't all go so smoothly once we move up in dimensions.
You got it. Taking 2n's Furstenberg and making it work in higher dimensions has some serious challenges. That well-spaced assumption that works like a charm in the plane. It doesn't really hold up in higher dimensions. And then there are these limitations with the Kakea maximal inequalities that make things even more complicated.
So is there a way around it? Do they just throw in the towel at that point?
Nah, they don't give up. They come up with this bold conjecture Meipel-Vine. It pushes the limits of 2n's Furstenberg inequalities. If they can prove this thing true, it'd have huge implications for the restriction conjecture in higher dimensions, which you can see in theorem point 10, where they directly link the two.
So even though the path gets a little rocky in higher dimensions, they've spotted a potential way forward.
Exactly. They introduced these concepts like the T-Frostman convex-Wolf axiom and the T-Frostman polynomial Wolf axiom as possible stepping stones to prove this bold conjecture. These axioms are like a framework for understanding how tubes are spread out in higher dimensions. And that's super important if you want to develop stronger Furstenberg-type inequalities.
Okay, so we're building this chain of conjectures, each one potentially getting us closer to that ultimate prize of cracking the restriction problem.
Right on. They even give specific examples like the SL2 example to show that their approach has legs and highlight some areas for further investigation.
But before we get too deep in the weeds, let's step back for a sec. What real progress have they made using this approach? In higher dimensions, I mean.
Well, they haven't completely cracked the restriction conjecture in higher dimensions yet, but they've got some pretty cool results. Take theorem point 17, for example. It shows an improvement for conjecture 1.1 in higher dimensions. It may not be the final answer, but it's definitely something.
So it's a step in the right direction, showing that their approach could really lead somewhere.
Absolutely. Every bit of progress, no matter how small, is huge in this area of math. It's notoriously tough.
And with that, we've made it through the introduction. This paper is definitely a dense one, and we've only just scratched the surface, ready to keep digging.
Let's dive into the details. I'm especially curious about how they handle incidence geometry and how they set the stage for proving that 2n's Furstenberg inequality in the plane.
Let's do it.
So section 1 here, it really takes us into this world of incidence geometry. It's all about how points and lines relate to each other, how they intersect. It's kind of wild how even in something as high level as Fourier analysis, these basic geometric ideas still matter so much.
Yeah, it's a good reminder that even the craziest math is built on like these simple building blocks. So how do they actually use incidence geometry to set up their approach?
Well, they start by introducing a bunch of key definitions and tools, laying the groundwork. One of the big ones is this idea of a refinement. It basically lets us zoom in on a specific part of the points or tubes, like focusing on a tiny detail in a big picture. This way they can analyze things at different scales and get more precise information.
It's kind of like using a magnifying glass to look at a really complex pattern,
Right.
focusing on different sections to understand the whole thing.
Exactly. And then they bring in these things called subsets, which can seem a little confusing at first glance.
I gotta admit, those symbols, they do make my head spin a bit. Can you break those down for us a little?
Think of these sets as a way to measure how spread out or dimensional a bunch of points are. Like imagine you sprinkle some dots on a piece of paper. If all the dots are bunched up close together, that's kind of like a low dimensional set. But if they're more spread out, that's more like a higher dimensional set. These subsets give us a precise way to measure that spread.
So the S is in that notation. That's representing the dimension of the set, even if it's not a whole number like the dimensions we're used to in everyday life.
Right. It's a more general way of thinking about dimension. It captures how the set changes as you zoom in or out.
I see. And then they talk about these uniform sets. It seems like it's all about keeping things organized and structured.
Uniformity is super important here. It means that the points or tubes are distributed in a nice, balanced way across different scales. That makes the analysis a whole lot easier.
So it's like making sure there aren't any crazy clusters or empty spaces. Everything's nice and even.
You got it. And to study these uniform sets, they introduce this branching function, which is kind of like a visual representation of how the set changes as you zoom in.
So if the branching function is really steep, that means the set is getting denser as you zoom in. But if it's flatter, then the distribution is more uniform.
Exactly. And they have this cool tool, Lemma 1.11, that lets them break that branching function down into smaller, more manageable pieces. It's like taking apart a complex machine to see how all the individual parts work.
It's amazing how they connect all these different ideas, refinements, subu, C subsets, uniform sets, branching functions, and this lemma. It's like they're building this whole framework for analyzing these incidence problems.
It really shows you how interconnected math is, and they don't stop there. They bring in this idea of point-line duality, which is pretty neat. It lets them switch back and forth between thinking about points intersecting lines and lines intersecting points, whichever is easier for the problem at hand.
So it's like a mathematical translator, letting them switch between different perspectives.
That's a great way to put it. This duality gives them a ton of flexibility in their approach. And then they introduce terms like shading and two ends. It's almost poetic.
It does sound a bit like math poetry, but what do those terms actually mean here?
Shading refers to specific regions inside each tube that they want to look at. Imagine highlighting certain parts of each tube. That's your shading. And the two ends condition, as we talked about before, means that these shaded regions are all clustered near the two ends of each tube.
Okay, so we're not just dealing with tubes anymore, but tubes that have these special octave zones, and those zones are crucial for using those two ends Furstenberg inequalities.
You got it. These concepts are like the foundation for how they approach these incidence problems that are at the heart of the restriction conjecture.
It feels like they're carefully building this really sophisticated toolkit in this section, like they're gearing up for the main event, proving that two ends Furstenberg inequality in the plane.
That's exactly right. With all these pieces in place, they're ready to tackle that challenge in section 2.
I'm ready when you are. Let's see how they unlock the secrets of that inequality. All right, let's jump into section 2. This is where they finally lay out the proof for that two ends Furstenberg inequality in the plane. It feels like we've been on this crazy journey, and now we're finally reaching the summit.
It's been quite a climb, for sure. Section 2 is packed with all these lemmas and propositions, all building up to that main result, theorem 2.1, that two ends Furstenberg inequality.
I noticed they kicked things off with lemma 2.3, which is all about these distinct tubes. What makes them so distinct anyway?
It's a subtle point, but it's important. They're saying two tubes are distinct if they don't overlap too much, like the overlap is small compared to their overall size. This helps them avoid counting things twice and get a more accurate estimate for the total number of tubes.
So it's like they're being really careful not to overcount by focusing on tubes that are truly unique in the space.
Exactly. And this idea of distinctness comes up again in lemma 2.4, where they build on lemma 2.3 to get an even better estimate for how many tubes are intersecting a certain region.
And then they bring in theorem 2.5, which they say comes from an earlier paper. It seems like a pretty powerful result with a lot going on.
Yeah, it's a key part of their proof. Theorem 2.5 basically sets up this either-or situation. Either there's a specific limit on the number of points, or there's this special scale where the set has a particular structure. It's like saying, Either the points are behaving nicely or they're arranged in this interesting pattern at a certain zoom level.
So they're kind of setting traps, forcing the tubes to reveal their secrets by how they're arranged.
Exactly. Then they take that powerful theorem and combine it with lemma 2.4 to get proposition 2.7. This gives them an even deeper understanding of how the lines and those shaded regions are configured.
It's really impressive how they're carefully building this chain of results, each one giving them a stronger grasp on the problem.
It's a perfect example of how math builds upon itself. And with Proposition 2.7 in their toolbox, they're finally ready to tackle Proposition 2.11. And as they showed us earlier, proving that 1 automatically proves Theorem 2.1, the 2n's Furstenberg inequality, at last.
It's like they've got all the puzzle pieces spread out, and now they're ready to put them together and see the full picture.
Exactly. And they go about this last step with a mix of really careful analysis and some pretty ingenious arguments. They use that multi-scale decomposition we talked about before, breaking the problem down into different scales and examining each one really closely.
I'm intrigued by their broad, narrow argument. Sounds almost philosophical. What's the thinking behind that?
It's a clever way to categorize how the lines are arranged based on how they're spread out. The broad case deals with lines that are well separated, while the narrow case deals with lines that are bunched up together.
So it's another way of imposing order on these potentially messy arrangements of lines. Breaking things down into these cases lets them take advantage of the specific characteristics of each configuration.
Right. This broad, narrow distinction lets them use the tools they've developed in a very precise way. And after carefully working through all these different scenarios, they finally arrive at the estimate they need for the size of the union of all the shaded regions. That's the Isabelle subterm in the theorem.
And with that estimate in hand, they've successfully proven Proposition 2.11 and therefore the 2n's Furstenberg inequality in the plane.
Yeah.
It's a huge accomplishment, and their approach is just so elegant, it's really captivating.
It shows you what you can do when you combine different mathematical perspectives and tools. By weaving together decoupling theorems, 2n's Furstenberg inequalities, and a deep understanding of incidence geometry, they've made some serious headway in figuring out this Fourier restriction conjecture.
It's like we've been on this amazing intellectual adventure, climbing the heights of mathematical creativity.
And we've only just begun. They go on to explore higher dimensional generalizations, put forward some fascinating conjectures, and really pave the way for future research in this exciting area of math.
This paper has been a real eye-opener, showing the incredible connections between analysis, geometry, and number theory. It's a reminder that even the toughest math problems can be solved with creative thinking and a lot of persistence.
Absolutely. And as we wrap up this deep dive, I'm left with this sense of wonder and excitement for what new discoveries are waiting to be made in this constantly evolving field of mathematics.
To all our listeners out there, I encourage you to check out the rest of this paper and really dig into this world of restriction theory. It might be challenging, but the rewards are definitely worth it.
Remember, as this paper shows us, the quest for mathematical understanding is a journey that's worth taking.
Until next time, keep exploring, keep asking questions, and keep pushing the boundaries of mathematical knowledge. All right, so today we're diving deep into restriction estimates using decoupling theorems and 2n's Furstenberg inequalities. It's a mouthful, I know. This paper by Wang and Shukun really tackles the Fourier restriction conjecture. And let me tell you, it's a fascinating problem that's had mathematicians going for, well, decades, really.
Oh, absolutely. It's a real brain twister.
Yeah.
This conjecture, at its core, asks, if we have some information about a function's Fourier transform, but it's restricted to a specific surface, can we actually say anything meaningful about the function itself?
It's like, imagine trying to figure out what an entire iceberg looks like, but all you can see is the very tip poking out from the water.
Yeah. You've got it. And what makes Wang and Wu's approach so intriguing is their use of, well, they might seem like really different tools at first glance. Decoupling theorems, and then this concept of 2n's Furstenberg inequalities. It's a pretty wild ride.
Yeah, and from what I gathered, they even go so far as to propose a whole new conjecture, a 2n's Furstenberg conjecture, which they think might be the missing piece, the key to unlocking the restriction conjecture. Pretty ambitious. But before we get ahead of ourselves, let's take a step back. Can you give us a little history lesson on this restriction conjecture? Where did it all begin?
Absolutely. The conjecture has a rich history, going all the way back to the work of Elias Stein. It all started with exploring the conjecture in two dimensions, the plane, which is where things are, usually easiest to visualize, to get a grip on.
Right, like when you're just starting out with geometry, you draw your circles and lines on a flat piece of paper.
Precisely. Then we had mathematicians like Pfefferman and Thomas who made some really significant strides, and their work led to, well, it's pretty famous in this area, the Stein-Thomas estimate. Think of it as like a cornerstone for this whole area of math.
Okay, so it's foundational, something to build upon. And then, wasn't it Bourgain who came along and introduced wave packet decomposition? That seems to be a pretty central idea in this paper.
Absolutely. Bourgain really shook things up with that technique. Imagine you're listening to a really complex sound wave, and then you have this tool that lets you break it down into all its individual frequencies. That's essentially what wave packet decomposition does for mathematical functions.
So you're taking something really complex and sort of dissecting it into smaller, more manageable pieces.
Exactly. And by analyzing those individual packets, we can start to really understand how the function behaves. Specifically, we can look at how the wave packets oscillate, and really importantly, how they interfere with each other geometrically. This leads us to, well, it's a whole other fascinating area, Kakeya-type problems.
Oh yeah, those geometric brain teasers. I remember something about needles and sets, but it's all a bit hazy, to be honest.
Essentially, Kakeya-type problems are all about, how efficiently you can pack lines or tubes into a given space. It might seem a bit abstract, like just a geometric puzzle, but they're actually deeply connected to the restriction conjecture.
Okay, starting to see some connections here, but now we're adding another layer of complexity with these decoupling theorems. How do those fit into this whole picture?
Well, decoupling theorems are all about understanding how different parts of a function's Fourier transform, how they interact with each other. We have to give credit to Wolff. He did some truly groundbreaking work in this area early on, and then later Bourgain and Demeter proved a major result, the et2 decoupling theorem. But in Wang and Wu's paper, the real star of the show is the refined decoupling theorem, theorem 0.3 in their paper.
Okay, let me see if I'm following this. So this theorem basically says if we zoom in on specific regions of a function, we can relate its behavior to these, well, they call them multiplicity factors, M&M.
You're right on track. Think of these multiplicity factors as a way of measuring how, well, I guess you could say tangled up things are. A high M means there's a lot of overlap, a lot of complexity. A low M suggests things are a bit more spread out, easier to analyze. And guess what? Estimating these factors involves tackling those Kakeya-type problems we were talking about.
So it all circles back. We're seeing how geometry, Fourier analysis, and these decoupling theorems all intertwine. Now, where does this 2n's Furstenberg inequality come into play? I have to admit, that's a bit of a mouthful.
It is a mouthful, but it's a really powerful tool. Imagine you're trying to understand how a bunch of lines intersect in a plane. This inequality helps us analyze those incidence problems, questions about how geometric objects intersect, and it's built upon this concept of Furstenberg sets.
Furstenberg sets, right. Those ring a bell, but could you refresh my memory a bit?
Sure, think of them as sets that have special properties related to how they intersect lines. The 2n's Furstenberg inequality, it gives us these tighter bounds on the multiplicity factor M, but only under certain conditions related to how the lines are spaced. It's like saying, if you arrange your lines in this specific way, then we can say something more precise about how they'll interact.
So it's giving us more control, more leverage to analyze these complex interactions. But how does this new inequality actually help us with the restriction conjecture itself?
That's the really exciting part. Wang and Wu, they suggest that this inequality could be a key to unlocking the restriction conjecture, not just in two dimensions, but potentially even in higher dimensions. Remember, the whole point of the conjecture is to understand what happens when we restrict Fourier transforms to specific surfaces. This inequality gives us a whole new way to analyze those restrictions.
It's like we're using geometric tools to sharpen our understanding of functions and how they transform. That's pretty wild. But things always get a bit trickier when we move beyond that familiar two-dimensional world, right? What happens when we venture into higher dimensions?
You're absolutely right. Higher dimensions always bring new challenges. But that's where theorem point 2 comes in. It's a significant result because it actually confirms the restriction conjecture in 3 dimensions, but for a specific range of values when n equals 3 and p is greater than 227.
And this theorem also has implications for Wolff's work on Kakeya sets, but in three-dimensional space this time, right?
Precisely. It implies Wolff's 52 hairbrush bound, which was a major result in the study of Kakeya sets. It's been holding strong since 1995. This connection just goes to show how what might seem like an abstract result can have really tangible consequences in related areas.
It's amazing how these different threads of mathematical thought, how they all weave together. But let's be honest, this is getting pretty mind-bending even for a deep dive.
Oh, definitely not light reading, that's for sure. But that's what makes these explorations so rewarding, right? We're really pushing the boundaries here.
And speaking of pushing boundaries, Wang and Wu don't stop there. They go even further and propose their own two-ends Furstenberg conjecture, laying the groundwork for a whole new avenue of research.
What's fascinating is that they're boldly extending the two ends Furstenberg inequality to higher dimensions, a move that could have major, and I mean major, implications. Conjecture point 9, they really meticulously lay it all out, and they even offer some compelling evidence linking it to the higher dimensional Furstenberg set estimate. It's really quite elegant.
Okay, you've piqued my curiosity. But why should we really care about this new conjecture? What's the potential payoff if it turns out to be true?
Well, if proven, and that's a big if, of course, this conjecture could completely revolutionize how we understand the restriction conjecture. Theorem 0.10 states that proving the two ends Furstenberg conjecture would actually directly imply the restriction conjecture itself. Can you imagine finally cracking a problem that's puzzled mathematicians for decades?
That would be absolutely monumental. But let's not get ahead of ourselves.
Yeah.
We still have a lot more ground to cover in this paper, especially those intricate proofs.
You're right, we've only just scratched the surface. There are a lot of fascinating details to uncover, particularly when we get into the specific techniques Wang and Wu use in their proofs.
Well, I'm ready to keep diving in. Lead the way.
All right, let's take a closer look at Theorem 2.1, which establishes that two ends Furstenberg inequality in the plane. It hinges on several lemmas and some really clever geometric arguments.
Before we get lost in the weeds, can you remind me what this theorem is actually saying and why it's so important?
Good point. It's easy to get bogged down in the details. So Theorem 2.1, it essentially gives us a lower bound for the sides of a set called EL. This set, it represents the points where lines in a specific collection intersect with their corresponding shadings, for lack of a better term.
Shadings. Okay. Can you elaborate on that a bit? I'm not sure I'm picturing that correctly.
Sure. Imagine each line has a kind of shadow or a region associated with it. The theorem says that the size or the measure of EL, which captures these intersections with the shadings, well, it's bounded below by a combination of factors. These factors include the density of the shading, a small parameter delta, and a specific exponent that's related to that two ends condition we talked about earlier.
So it's giving us a way to quantify how spread out these shaded intersections are, taking into account the spacing of the lines and how dense their shadows are.
Exactly. And the proof of this theorem, it really relies on several lemmas that deal with different aspects of this whole geometric setup.
Let's dive into those lemmas then. What about lemma 2.3, the one you mentioned earlier? What's the key takeaway there?
Lemma 2.3 focuses on a specific scenario where we've got a collection of delta balls and tubes intersecting them. It gives us a lower bound on the number of distinct tubes involved, and that bound depends on parameters like the thickness of the balls and tubes, and a parameter r, which represents the minimum number of tubes per ball.
So it's another way of quantifying the richness, I guess you could say, of these intersections, but this time focusing on balls and tubes instead of lines and shadings.
You got it. And the proof of this lemma relies on a clever use of the Furstenberg set estimate, that concept we discussed earlier. Remember how those sets have those unique intersection properties?
Okay, so we're already seeing how these different tools and concepts are starting to connect. What about lemma 2.4? Where does that fit in?
Lemma 2.4 builds upon lemma 2.3, but introduces a scaling factor, delta. Think of it like zooming in or out of our geometric configuration. The lemma basically states that the lower bound on the number of distinct tubes, well, it scales accordingly as we change our perspective.
So it's like a zoom lens for our incidence estimates, letting us analyze the problem at different levels of detail.
Precisely. And this scaling property turns out to be really crucial for proving the main theorem.
Okay, I'm starting to see how these pieces fit together, but I have a feeling it's about to get even more intricate.
You're not wrong. The next piece of the puzzle is Theorem 2.5, a powerful result from a previous paper by these same authors. This theorem deals with a more complex setup involving lines, shadings, and now a set of delta balls.
And this theorem presents us with two possible outcomes, right? It's like a fork in the road.
Exactly. The first outcome provides a lower bound on the number of delta balls, similar to what we've seen in the previous lemmas. But the second outcome, this is where it gets interesting, introduces a new concept, a scaling factor, delta, that characterizes how the delta balls behave at different scales.
So it's like saying either our delta balls are densely packed together or they exhibit a specific kind of self-similarity as we zoom in or out.
You got it. And this dichotomy turns out to be very powerful for analyzing the problem.
All right, I'm ready to see how this theorem works its magic and how it ultimately leads to the proof of theorem 2.1.
It all boils down to how we use this theorem to analyze the size of EL, that set of intersection points we were discussing. Remember, we're trying to prove that its size is bounded below by a specific expression. And to do that, we use a clever combination of theorem 2.5 and lemma 2.4, which gave us that handy scaling property for the number of distinct tubes.
Sounds like we're building up quite the toolkit for tackling this problem.
Indeed we are. And the next step is to take the insights from theorem 2.5 and lemma 2.4 and, well, bring them together. That's where proposition 2.7 comes in. This proposition basically lays out 3 possible scenarios for our geometric setup.
3 scenarios. This is starting to sound like a choose-your-own-adventure for mathematicians.
In a way, it is. Each scenario leads to different implications for the size of EL. The first scenario gives us a direct bound on the number of lines intersecting at a given point. The second scenario provides a more general bound on the size of EL itself. And the third scenario, well, it throws another scaling factor into the mix.
Ah, those scaling factors. Always popping up to keep things interesting.
They're essential, though. They allow us to analyze the problem at different levels of detail and eventually to piece together a complete and rigorous picture. Now, to prove proposition 2.11, which is the stepping stone to theorem 2.1, we need to use a technique called backward induction.
Backward induction. Isn't that a bit counterintuitive?
It might sound strange, but it's a really powerful technique. Imagine you're at the finish line of a race, and you want to make sure you can always get back to the starting line. So you work backward, step by step, to ensure there's always a path. That's the idea here. We start with a base case, where the parameter delta is very small, and we assume the proposition holds true. Then we show that if it holds for a smaller delta, it must also hold for a slightly larger delta.
So we're working our way up from the smallest scale to prove it's true for all values of delta. Clever.
Exactly. And throughout this process, we use those 3 scenarios from proposition 2.7 to carefully analyze the size of EL under different conditions. It's a delicate balancing act.
All right, I'm ready to see this balancing act in action. Let's dive into the proof of proposition 2.0:1.
The proof itself is divided into 7 key steps. But instead of going through each one meticulously, let's focus on the overall strategy and highlight the key insights.
Sounds good to me. Efficiency is key.
Absolutely. So the first step involves using something called a multi-scale decomposition. Essentially, we're breaking down the problem into more manageable chunks, each characterized by a specific scale. It's like organizing a messy room into neat little boxes.
So it's like creating a filing system for all our geometric objects.
Precisely. Then, in step 2, we perform a uniformization of EL inside each of these boxes. This means we're finding a refinement of EL that has some desirable properties, which will make it easier to analyze.
Always a good idea to tidy things up before you really start digging in.
Exactly. Then comes step 3, which is often called the broad-narrow argument. We cleverly partition the problem into 2 distinct cases. In one case, the intersections are broad, meaning they're spread out over a large area. In the other case, they're narrow, concentrated in a smaller region.
The classic divide and conquer strategy.
It's a powerful technique that pops up all over mathematics. By separating these cases, we can use different tools and arguments that are specifically tailored to the geometric properties of each scenario.
Okay, so we've divided the problem into broad and narrow cases. What's next on our agenda?
In step 4, we focus on the broad case. We show that if the scale we're working with is large enough, we can directly apply something called corollary 2.8, and that allows us to wrap up the proof for that particular scale. Corollary 2.8 basically gives us a nice bound on the size of EL, but only under certain conditions.
So if things are spread out enough, broad enough, we can take a shortcut and finish that part quickly.
You got it. But if the scale is smaller, if things are more concentrated, then we need to roll up our sleeves and delve a bit deeper. That's what step 5 is all about. This step involves setting up a whole new incidence problem. but this time it's inside each of those boxes we created earlier. We're analyzing how the delta balls and tubes are interacting within that smaller, confined space.
So it's like zooming into one of those boxes and discovering a whole new world of geometric complexity.
Exactly. We introduce a new set of tubes, TB, and their associated shadings to represent these interactions within the box. Then, in step 6, we carefully analyze the properties of this new configuration, breaking it down into even smaller subcases.
Subcases within subcases. It's turtles all the way down.
It can definitely feel that way sometimes, but the important thing is to stay focused on the ultimate goal, proving proposition 2.11. We need to analyze every single possibility, every scenario, to make sure our argument is completely airtight.
And then, in step 7, we finally put all the pieces together to estimate the size of EL. It's like the grand finale.
Exactly. Depending on which subcase we end up in, we apply different techniques and inequalities to obtain the lower bound we're looking for. It's like a grand symphony of mathematical arguments with all the previous lemmas, theorems, and ideas coming together in harmony.
Okay, I'm really curious to hear how these different subcases play out and how they ultimately lead to the proof of proposition 2.11. Shall we delve into those now?
Absolutely. Let's explore those subcases and see how they bring us closer to proving this crucial proposition.
All right, so let's unpack these subcases, those different paths in step 7 of the proof for proposition 2.11. They all lead to that same conclusion, right? It's pretty neat how they all come together.
Exactly. It really is remarkable how Wang and Wu have managed to weave together these different scenarios and arrive at a unified result.
So let's start with case A. What's the main idea there? What are we trying to do?
In case A, we're dealing with a situation where we have a good understanding of how many lines, those denoted as L6, how many of them intersect at a given point. We use that bound along with the properties of those refined shadings, those are denoted as Y6, to establish a lower bound on the size of EL, that stat we've been talking about.
Okay, so if the intersections are not too, cluttered, we can get a good handle on the size of EL directly. Makes sense. What about case B then? How does that one differ?
Case B, it offers a more, I guess you could say, a more global perspective. Instead of zeroing in on those individual intersection points, we look at bounds on the size of EL, but within each R-ball. Remember those from our earlier discussions about tubes and balls?
Right, those R-balls were important for analyzing how those geometric objects interact with each other.
Exactly. So by taking those bounds, the ones for each R-ball, and adding them all up, we get a lower bound for the overall size of EL. It's like piecing together a big puzzle, a global picture, but from a bunch of smaller local snapshots.
I like that analogy. Now, case C, that's the one where we had that extra scaling factor DD, right? If I'm remembering correctly.
You get a sharp memory. Case C is where things get a bit more, nuanced, I suppose. This new scaling factor, B, which is larger than that previous scale, R, it lets us zoom out even further. We can examine how EL interacts with those neighborhoods around the lines in our collection L6.
It's like using a wider angle lens to capture a broader perspective.
Precisely. And by analyzing this zoomed-out view, we can establish a bound on the size of EL that takes into account the density of the shading and also the behavior of that new scaling factor. It all comes into play.
It's really fascinating how each of these cases gives us a different lens, a different way of looking at the same problem. But in the end, they all lead to the same result.
Exactly. That's the beauty of this proof, the elegance of it. No matter which path we choose, which case we analyze, we arrive at that same conclusion that the size of EL is bounded below by that expression in proposition 2.11. It's like imagine 3 rivers all flowing from different sources, but eventually merging into a single powerful stream.
That's a great way to put it. So by proving proposition 2.11, we've locked in that 2n's Furstenberg inequality in the plane. And as you mentioned earlier, this has big implications for understanding incidence geometry and really a whole bunch of related problems in harmonic analysis.
Absolutely. Theorem 2.1, which comes directly from proposition 2.11, it really gives us this powerful tool to analyze those intricate relationships between geometric objects and how they intersect. It's a game changer.
Okay, so we've conquered Theorem 2.1 and its proof. What's next on our journey through this paper?
Now let's shift gears a bit and move into higher dimensions. Remember theorem point 2, the one that confirms the restriction conjecture when n3 and p is greater than 227?
Right, that was a big deal because it was the first time the conjecture was confirmed in 3 dimensions for that specific range of values.
Exactly. And to really appreciate why this result is so significant, we need to dive into the connection between the restriction conjecture and, you guessed it, Kakeya-type problems.
All right, I'm ready for more geometric puzzles. Kakeya sets always seem so intriguing to me.
They are fascinating, and it turns out they're very deeply connected to the restriction conjecture. But to understand this connection, let's first make sure we're all on the same page about what a Kakeya set in 3 dimensions actually is. Definitions are important, right?
Absolutely. Let's get those definitions crystal clear.
So, a Kakeya set in R3, it's a set that contains a unit line segment, but in every single direction. Imagine like a magical needle that can rotate freely in 3-dimensional space. A Kakeya set is basically any region where you can fit that needle no matter how you rotate it.
Okay, I'm picturing it. So how do these Kakeya sets, these regions that can fit our magical needle, how do they relate to the restriction conjecture? That part still seems a bit mysterious.
The connection is this. Understanding the size, or more precisely the Hausdorff dimension of Kakeya sets, it's closely related to proving the restriction conjecture. They go hand in hand.
Hausdorff dimension. Okay, that rings a bell, but can you refresh my memory?
Of course. Hausdorff dimension, it's a way to measure how rough or how fractal a set is. It's kind of a generalization of our usual idea of dimensions. Points have dimension 0, lines have dimension 1, planes are 2-dimensional, and so on. But Hausdorff dimension, it lets us assign fractional dimensions to more complex sets, like those wild fractals.
Right, those amazing shapes that are self-similar at different scales, like snowflakes and coastlines.
Precisely. So figuring out the Hausdorff dimension of Kakeya sets, it's a really challenging problem. But it turns out if we can prove a specific bound on their dimension, we can also prove the restriction conjecture. It's like a 2-for-1 deal.
So solving one puzzle unlocks the solution to another. I love how interconnected math is.
Exactly. And theorem point 2, remember, the one that confirms the restriction conjecture for n3 and p greater than 227? Well, it also gives us a new bound on the Hausdorff dimension of Kakeya sets in 3 dimensions. This bound is called Wolff's 52 hairbrush bound, and it was a huge breakthrough when Wolff first proved it back in 1995.
So Wang and Wu's result, it's not only advancing our understanding of the restriction conjecture, but it's also pushing forward our knowledge of these fascinating Kakeya sets. It's amazing how these different areas of math are so intertwined.
It really is a testament to the interconnectedness of mathematical ideas, and that's what makes this feel so captivating. There's always something new to discover, and oftentimes a breakthrough in one area can shed light on a seemingly unrelated problem in another.
Okay, I'm starting to see how theorem point 2 bridges that gap between the restriction conjecture and these Kakeya sets. But I have a feeling we're just scratching the surface here. Maybe we should dive deeper into the proof itself to really grasp how those connections work.
You're right. The proof is where the real magic happens, and it's a bit intricate, involving several steps and some very clever arguments. But I think it's worth the effort.
Well, I'm game if you are. Lead the way.
All right, let's start by looking at the first key step in the proof. It involves using the refined decoupling theorem. Remember that one?
Ah, yes, the refined decoupling theorem. That powerful tool that relates a function's behavior to those multiplicity factors, m and m.
Exactly. Remember, those multiplicity factors, they essentially capture how complex the interactions are between different parts of a function's Fourier transform. And in this proof, we're going to use the refined decoupling theorem to analyze the Fourier transform of a specific function. It's called the extension operator.
Extension operator. Interesting. What exactly does that do?
Think of the extension operator as a way to, well, extend a function. It takes a function that's defined on a surface and extends it to be defined in the entire space. It might seem a bit abstract at first, but it's a very crucial tool when we're studying the restriction conjecture.
Okay, so we're taking a function on a surface and sort of blowing it up so it's defined everywhere.
That's a good way to visualize it. Now, the refined decoupling theorem, it comes in to help us analyze the behavior of the extension operator's Fourier transform. It lets us break down the Fourier transform into smaller pieces and see how those pieces are interacting with each other.
So it's like taking a complex piece of music, a whole orchestra playing, and separating it into individual instrumental parts so we can understand each one better.
Precisely. And by understanding those individual parts and how they work together, we can gain a deeper understanding of the whole of the extension operator's Fourier transform in this case.
Okay, so we've used the refined decoupling theorem to break things down into smaller, more manageable pieces.
Yep.
What's the next step in our puzzle?
The next step is where that 2n's Furstenberg inequality really shines. Remember, this inequality gives us a way to control the number of intersections between certain geometric objects, specifically lines, and their associated shadings, those regions we talked about earlier.
Right, those shadings were like shadows or regions associated with each line.
Exactly. And in this proof, we're going to use that 2n's Furstenberg inequality to analyze the intersections between tubes. But not just any tubes. These are tubes that are associated with those different pieces of the extension operator's Fourier transform. We're taking that geometric tool and applying it to the frequency domain.
Whoa. Okay, so we're taking those geometric ideas and applying them to the Fourier transform. It's like we're blending geometry and analysis together.
Precisely. And by carefully controlling how many times those tubes intersect, we can establish that restriction estimate we've been aiming for. And as we discussed earlier, that estimate directly leads to Wolff's 52 hairbrush bound on the Hausdorff dimension of Kakeya sets. It's all connected.
It's like a chain reaction, one result leading to another, and suddenly we're making progress on a problem that's been around for a long time.
Exactly. That's what makes this paper so groundbreaking. Wang and Wu, they haven't just made significant progress on the restriction conjecture itself, but they've also given us new tools, new techniques that could have major implications in other areas of mathematics.
Speaking of implications, let's shift gears and talk about that bold new conjecture they proposed, the 2n's Furstenberg conjecture. They seem to think it might be the key to unlocking the restriction conjecture in even higher dimensions, which is a pretty big claim.
It's definitely a bold claim, but their work provides some very compelling evidence to support it. They lay out the conjecture very carefully in Conjecture 0.9, and they've even provided supporting evidence linking it to the higher dimensional Furstenberg set estimate. It's not just speculation, there's real substance behind their proposal.
So they're not just throwing ideas out there, there's real mathematical rigor behind it.
Absolutely. And if their conjecture turns out to be true, it could completely change our understanding of the restriction conjecture. Theorem 0.10 explicitly states that proving the 2n's Furstenberg conjecture would directly imply the restriction conjecture. Imagine finally solving a problem that has puzzled mathematicians for decades.
That would be absolutely incredible. It'd be a major breakthrough. It really shows you the power of creative thinking and how different areas of math can come together in unexpected ways. Who would have thought that geometric tools, like that 2n's Furstenberg inequality, could help us understand functions and their Fourier transforms?
It really is a beautiful example of the elegance and interconnectedness of mathematics. There's always something new to discover, and often it's the most unexpected connections that lead to the most profound insights.
Okay, I think we've covered a lot of ground here. Maybe we should take a little break and let our listeners digest everything we've discussed so far. It's a lot to take in, even for those who are already familiar with these concepts.
Excellent idea. We'll pick up our exploration in the next part of our deep dive, and we'll see how all of these pieces come together to solve this long-standing mathematical puzzle.
Okay, so we're back, ready to wrap up our deep dive into Wang and Wu's paper. It's been quite a journey, exploring these restriction estimates, decoupling theorems, and those, well, I'll admit they're still a mouthful, those 2n's Furstenberg inequalities.
It's a lot to take in, for sure, but the payoff is, well, it's pretty huge, and you see how it all comes together.
Right, like how those geometric tools help us understand something as abstract as the behavior of functions in the frequency domain.
Exactly. And remember where we left off, we are about to delve into how that 2n's Furstenberg inequality is used in the proof of theorem point 2. That's the one that confirms the restriction conjecture for n3 and p greater than 227, a pretty big deal.
Right, and that theorem, it connects to a Wolff's 52 hairbrush bound, which basically puts a limit on how thin those tubes can be if they want to intersect in that specific way. It's mind-bending, but also really elegant.
It is. So to get to that bound, to really prove it, we need to carefully analyze how those tubes, the ones associated with the different pieces of the extension operator's Fourier transform, how they intersect with each other. That's where that 2n's Furstenberg inequality steps in, and, well, it really saves the day.
It's like we're using this geometric tool to, to untangle this really complex web of interactions that's happening, but in the frequency domain, not in the usual geometric space we're used to thinking about.
That's a great way to put it. The 2n's Furstenberg inequality, it gives us a way to control how crowded those intersections can get. It tells us that if the tubes are arranged in a specific way, with certain spacing conditions, then those intersections can't be too dense. There has to be some breathing room.
So it's like those tubes are all trying to squeeze into the same tiny space.
Yeah.
And the inequality is like, hold on, spread out a bit.
Exactly. And this control, this ability to say something about how densely those tubes can intersect, it's crucial, absolutely essential for getting to that restriction estimate we're after.
Okay, I see the connection now. But I have to admit, trying to visualize these tubes intersecting in 3 dimensions, it's a bit of a mental workout.
Oh yeah, it's definitely a challenge to picture in your head. But the key takeaway, the thing to really remember, is that the 2n's Furstenberg inequality gives us the leverage, the mathematical muscle, to get a handle on these interactions and finally derive that restriction estimate. And that estimate, remember, that's the bridge, the direct link to Wolff's bound on the Hausdorff dimension of Kakea sets. It's all connected, all part of this beautiful tapestry.
It's like a domino effect. One result knocking over the next, and suddenly we're making real progress on this problem that has stumped mathematicians for such a long time. It's quite exciting.
It really is, and that's what makes Wang and Wu's paper so groundbreaking. They haven't just made progress on the restriction conjecture itself, which is already a huge accomplishment, but they've also given us new tools, new techniques, new ways of thinking that could ripple out and have a big impact on other areas of mathematics. It's more than just a single result. It's opening up new possibilities.
Speaking of new possibilities, we have to talk about that bold conjecture they proposed, the 2n's Furstenberg conjecture. It's quite a claim, suggesting it could be the key to finally unlocking the restriction conjecture, but in even higher dimensions. It makes you wonder what other mysteries are out there waiting to be solved.
It is a bold conjecture, no doubt about it. But their work, it lays out a really strong case. They've carefully outlined the conjecture in Conjecture Point 9, and they've even presented some pretty convincing evidence linking it back to the higher dimensional Furstenberg set estimate. It's not just a shot in the dark, there's some real mathematical meat behind their proposal.
So they're not just throwing ideas out there hoping something sticks.
Yeah.
They've done their homework and it shows.
Absolutely. And if their conjecture turns out to be true, well, it could be revolutionary. I mean, truly revolutionary. Theorem point 10 states that proving their 2n's Furstenberg conjecture would actually imply the restriction conjecture. It would be a direct path to a solution, and that would be a monumental achievement in the field. It would be, well, historic, really.
It's incredible to think about. A problem that has puzzled mathematicians for decades, and maybe, just maybe, this conjecture holds the key to finally cracking it wide open.
And if it does, it really highlights the power of creative thinking, of looking at problems from new angles, of connecting ideas that might seem completely separate at first glance. Who would have guessed that geometric tools like this 2n's Furstenberg inequality could be the key to understanding something as seemingly abstract as the behavior of functions and their Fourier transforms? It's a testament to the beauty and the surprising interconnectedness of mathematics.
It really is. It makes you wonder what other connections are out there just waiting to be discovered. What other seemingly unrelated areas of math might hold the key to unlocking some of the biggest mysteries in the field?
It's a great question to ponder, and I think that's what makes mathematics so captivating. There's always something new to learn, something new to explore, and who knows, maybe one of our listeners will be the one to make that next big breakthrough.
That's a great note to end on. So to all our listeners out there, keep those minds curious, keep asking questions, and keep exploring the fascinating world of mathematics. We've covered a lot of ground today, from restriction estimates and decoupling theorems to those intriguing 2n's Furstenberg inequalities. And I hope you've enjoyed this deep dive as much as we have. Until next time, keep those pencils sharp and happy mathing.